along with a couple of quizzes to make sure we're on point and practicing our methodology. And to that end, then we start with passage number 1. So I'm going to give you 2 minutes. I want you to read through passage number 1. I want you to think about your roadmap. Make sure to preview it first. And I want you to think, does this seem like a passage that you would handle first or second when you're going through your MCAT? Does this look like something you might handle now or handle later based on the topic and based on the time? Then when you're done, we'll talk about your roadmap and apply the roadmaps you come up with to some questions to really focus again on our critical thinking strategy, learning how to dissect the questions a little bit more successfully. See you guys back here then in 2 minutes after you've had a chance to read, preview, and triage passage number 1. Okay, team. Talk a little bit about your roadmap. What type of passage is this one? What type of passage is this one? Yeah, we got ourselves a nice little experimental passage. Lots of experiments, lots of headers to point us that way, which is good to find out. And as we go through, there are definite things we don't want to miss in this experimental passage. Notice there are lots of equations. So again, worthwhile for us to map what the equations tell us. The first equation, we're watching just decomposition. Hydrogen peroxide makes oxygen and water. If we throw some iodide in there, then we're going to end up with some, we'll catalyze it, and we can see how we catalyze. Now, I want you to look at this reaction mechanism, though. It says iodine is a catalyst. What does that mean? What do you see then? How can you recognize iodine as a catalyst in this reaction mechanism, in mechanism 1? And yeah, it starts at the beginning and it ends up unchanged at the end. A good sign that you have a catalyst. So if we're looking at a reaction mechanism, we can see the catalyst. They start off in the reactants, they end up in the products, they're regenerated after being used, right? Because they're like biological enzymes that we talked about in Bio 1. Catalysts speed up a reaction without actually being used up in the reaction itself. So since it's being used and then be regenerated, that makes it a nice catalyst. And then the chemistry student starts to study. Now, when we see the chemistry student, what's the first thing that goes into your head? Yeah, when you see students, fair or not, the MCAT tends to have the students make the mistake. Now, are we going to be reading actively to find the mistake? No. But when we get to questions, we won't be surprised if we see mistakes being made. So we go to experiment 1. Notice here, experiment 1, what was the goal? What was the goal of experiment one? What does the data in experiment one or table one try to give us here? Because we know in experiments we want to read for the goal. Yeah. Michael, O2 formation, Rouge, measure O2, measure O2, measure O2, absolutely. Throw some iodide in and let's watch H2O2 decompose by measuring the rate of O2 formation. There it is. And if we need the numbers, we've got those in table one. Now experiment two, were you surprised by the details of experiment two? No. Here comes what we expected. The student made a mistake. And turns out he or she has a hypothesis. They suspect that acid may have been present. So let's go test this hypothesis. So you know what? We already know the goal of experiment three. What's that going to be? What's that going to be? And there's, yeah. If the experiment two had a mistake, then experiment three, let's test using acid. Throw some acid in and see if the exact expected response occurs. And that's exactly what we do. Repeat experiment one, throw in now nitric acid, and instead of watching O2, let's watch I2, since that will be a product different than what we expected. Noting now, iodine's not really acting as a catalyst, it's completely undergoing reaction. Something to keep in mind. So we throw in a little bit of nitric acid and see how that affects it. Now, when you read that last paragraph, then what's something that kind of jumped off the page? And I like where Anne was going. It's a nice little side, oh, this makes sense. What do you notice in this particular and there it is. Yeah, Cynthia, notice they give us a rate law. They give us a rate law for experiment 2 and 3, noting that the rate depends on protons, and the rate depends on iodine, and the rate depends on H2O2, which is no surprise. If we change any of those reactants, we're going to affect the rate itself. Now, were we given a rate law for experiment 1? We were not. So do you think the MCAT might ask us to go and find that rate law? And Michael, I love the fact that no, but you know we can find it. And that's a very fair question. If they give us the results of the data, if we have experimental data, we can find the rate law. Now, sometimes, and note, when you're reading, I don't ever want you to challenge what the passage is saying. So Anne's question is a good one. Lots of times we'll read a passage and think that detail doesn't sound right. But if the passage says it, we assume it to be absolutely 100% true. Questions may ask you and say, you know what, it turns out it was wrong, find the new one. That's possible. However, you shouldn't go in reading assuming that something you read was wrong. So it's very possible that they could say, you know what, that rate law turned out not to be right. Let's go find the real one. However, without a question along those lines, if it's in the passage, we assume it to be true until something tells us otherwise. And then we have a mechanism, a step-by-step mechanism to explain how acid is going to yield the overall reaction to create iodine and the different steps of it. So we go to question 1 and we think, notice, all the answer choices are rate laws. We have the rate constant K and different components. The question here, though, is asking us for the rate law for which experiment? Yeah, we want experiment 1. So, and Ann just said the magic word. Where can we go to get the data to find that rate law? Well, we go to table 1. But you know what? Even as an expert, we can go one step back. One of these is a trap. Which of these would you eliminate automatically on test? They never give it a second look because you know it's just there to cost us some points. And there it is. The one with B. Why would you get rid of B? Why do we know that B is there as just a trap for the person who didn't read but is just trying to go find details? And there it is. B is experiment 2 and 3. Experiment 2 and 3 had acid in them. Experiment 1 didn't. So a rate law can't depend on acid if there's no acid present in the reaction. So acid more shouldn't be in the rate law. You guys got it. So we go to table 1. Because if you need a rate law, then you have to watch for the result, or you have to have data results. And so note, we're going to change concentrations and ask, how does that affect the rate of what we're measuring? And I want you to think about it like a scientist. The easiest way to determine the effect is to change one thing at a time. Like if we go from trial 1 to trial 2, note, that concentration of H2O2 changes by a factor of 2. So we're going to change the concentration of H2O2 by a factor of 2. And the question should be, when I change B, how does that affect the rate? So if you look at the rate here, how is that affected? Well, if we double H2O2 from 0.04 to 0.08, notice how the rate goes from 3.6 to 7.2, almost exactly doubled. And that's going to be perfect. So note the rate has doubled. Now, this is what a rate law is asking. There is, and you saw this in your homework in the workshops for today, there is an exponential relationship between your concentration change and your rate law. So we've got to ask, what is the exponent that relates the change in H2O2 to the change in the rate? What exponent makes this equation equal? So what number do we raise 2 to get 2? X has to be 1. So note, it is first order with respect to H2O2. And that's helpful. We can start eliminating again, and we know that it's not answer choice D. They're directly proportional, nice one-to-one relationship. So you tell me, now we've got to look for iodine. Is there one experiment where only iodine changes, but H2O2 does not? Yes, we can do 1 and 3, we can do 2 and 4. Should it matter which one we choose? If we go from 1 to 3 or 2 to 4, should it matter? Nope. You're going to get the same exponential relationship either way. So we'll look from 1 to 3. From 1 to 3, we increased our iodine concentration by a factor of 2, or by a factor of 1.5 rather. How did that affect the rate as you went from experiment 1 to experiment 3? Well, if we increase the concentration by 1.5, notice also the rate's 1.5. It doesn't say the same. It doesn't double. Looks like it's right there in the middle. So it's not quite 7.2. It's not 3.6. 5's got to be right there in the middle. So what is our exponent then that relates 1.5, or the change in the iodide, to 1.5, the change in the rate? And notice this exponent again is going to be 1. So there's our rate law. We know it's first order with respect to the iodide. It's first order with respect to H2O2. And when it comes to a rate law, there's always a K. So now we've got a prediction. We can match that nicely to answer choice A. So for rate law experimentation, you will need a table. Does this look like a question you might do the first time you see it, or maybe before you leave the passage? Yeah, this is probably a good one to go before you leave. It takes a little bit longer, but it's not necessarily harder. It's just remembering that it's an exponential relationship between the rate and the change itself. So it makes it easier. Plus, if we go to a question like number 2, we'll find number 2 is a whole lot quicker. When you see these answer choices, step 1, step 2, step 3, step 4, that's a humongous clue. What are we going to need to use to solve this question without a shadow of a doubt? What do we need for this? And guess what? If we see step 1, step 2, step 3, step 4, that should immediately make us think of mechanism 2. And when we think about the question, we want the slow step in experiments 2 and 3. So guess what? We do need that mechanism. But again, we think, draw it out. What could we translate in that question stem to make a little more sense of it? There's a phrase or a term in there that's giving us a nice clue beyond where to go look. It's the slow step. You guys respond. Slow step just means rate determining step, or RDS. So what part of the passage will be particularly helpful in me finding the rate determining step? Yeah, or the rate law. The slow step is the step you use to find the rate law. So guess what? We have the rate law. It tells us point blank that the rate law depends on protons, on iodine, and H2O2. So the slow step is our rate determining step. It finds our rate. We've got to ask what needs to be in that rate. So I want you to look at these components and think, where should these concentrations show up in a reaction if the reaction depends on all of them being present? Does it need to be in the products or in the reactants? If this reaction needs protons and iodine and H2O2 to continue. And there it is. Note, these all need to be reactants in one step for it to be the slow step. Now, if you go look at all four steps, you'll notice there's no step that shows protons and iodine and H2O2, but there's got to be a step that incorporates them all. So we can go one by one. Look at step one. Does step one incorporate hydrogen peroxide and acid and iodine? Nope, so it can't be step one. Iodine's missing. What about step two? Will step two utilize H2O2 and iodine and protons? Because all three have to be there. And notice, there it is. It came right here from step one, right? We take H2O2 and hydrogen, we make the H3O2, and we put it with iodine. So guess what? Pop that proton off, and there it is. So what's our answer? At that point, we're done. We just select B and move on our way. Done. Done, done, done. Now, note, and Sandy's asked a good question. The exponents here won't affect which step is your slow step. The exponents just show you the relationship between. The rate law itself will show you the absolute necessary components. The exponent will show you the actual numerical relationship between them. So had there been exponents here, it wouldn't have affected it in any way, shape, or form. The slow step still needs the same reactants. How those reactants will actually numerically change the rate, that's what you get from those exponents. And then note step 3 has no H2O2, step 4 has no iodine, so it's got to be step 2. That's done. Number 3, and again, notice reaction types. One of the easiest or one of the easiest general chemistry questions you can encounter on the MCAT is describe the type of reaction. There are some that you read for today, you've got to know those and know them cold because they're going to make a big difference. Like here, where are we going to go to find the answer for this? Where are we going to go to find the answer for number 3? Yeah, let's go right back to mechanism 2 in our brain. So we look at mechanism 4. And we got to think, what type of reaction is this? If I take my proton, I take my hydroxide, and I make some water. Notice it's got to be one of the 4 choices given up here. And notice, yeah, guess what? It's just going to be neutralization. Take your acid, take your base, put them together. Normally, we're used to looking at neutralizations as acid plus base makes salt and water. But if you take the basic acid component, proton, the basic base component, hydroxide, there's nothing there to make a salt with. It's just an acid and a base, and we're done. So question. Or no, rather, questions 2 and 3. Can we do 2 and 3 in the time it took to do question 1? Without a doubt. That right there shows you why the MCAT wants us to triage. There are going to be questions that take a while, but you know what? If it's going to slow me down from getting a whole lot of other points, then I'm not going to worry with it. Question 1 was good for a second pass in the passage. 2 and 3 were good for now. Look at number 4. We're obviously going to be solving for mass. Think, is this good for now, for before we leave the passage, or perhaps even when we're done with the entire test? When do you think you might do this one? Because no, we want to have the maximum mass of I2 from trial to experiment 3. Well, let's think about it, right? It's good to approach a question, to think a little bit about it before you make that jump. Because sometimes the MCAT can hide a hard question in an easy one. Or make an easy one look hard, rather. So what do you think? What kind of info are we going to need to solve this if I want to get the amount of I2 formed from experiment 3? One, if I want to get grams, I'm going to do mole of I2, without a doubt. How am I going to get moles of I2? What do I need to get moles of I2 so I can convert that to mass of I2? I'm thinking about the maximum mass. I need molecular weight. I need grams of I2. But think about it. Do I need anything else to get 2 moles of I2 and grams of I2? I want to solve for I2. How much information do I need to solve for that? What do we need to set up? 1, we need a reaction. So 1, we need a reaction and we need to balance it so we can get that molar ratio. Absolutely. What else do you need? We're going to have to set up a reaction equation. And Michael, we'll need reaction concentrations. Now, will every one of those reactants be necessary for us to find how much I2 we can form? No, only the limiting reagent. Does the passage tell us which of them is limiting? Well, back, how many reagents are there that we get for experiment 3? Yeah, we go back there is, we look back at experiment 3 and experiment 2, there is nitric acid, there is potassium iodide, there is H2O2. So we have 3 reagents and they give us volume. So note, for us to solve this one, we're going to have to set up a balanced equation. Then we're going to have to find our limiting reagent, and it turns out our limiting reagent here is potassium iodide. And then we're going to have to convert, where we go from potassium iodide over to grams of iodide, and then we're done. And Dalton, that is exactly what I wanted you guys to think about this one. This one is really lengthy. Does the MCAT put questions this lengthy on test set? You bet. Why? Why is this question on the test? Because there's no way to make it quicker. This is a 5-6 minute question. It's got a lot of work, a lot of steps, a lot of math. And there it is. Slow you down, make you panic, shake you up. This is the broken toe of the MCAT. Dealing with a broken toe isn't the fastest procedure, but if you handle the broken toe the second you see it, you may very well miss the heart attacks that needed you that came in after it. This is crisis prevention 101. Good doctors know where their time goes. This question is just there then to slow you down. This should be done at the end of the entire test when all the other questions are done, because the other questions won't take this long. How many questions can honestly be on the exam that take you this long to solve? 3, and there is Adam. 1, 2, tops. If there are 5, 6 questions this long, then you know what? That means there's no way to finish the test on time. There can be 1 or 2 tops. However, you know there's going to be more than 1 or 2 based on math. So what does that tell you about math questions in general? Will every question involving math always be this long? And Dalton, yeah, 1 or 2 per section. Primarily in physical sciences is where these are going to show up, because it's harder to come up with a longer question like this in some of the other sections. But there it is. If there are more questions with numbers than there are questions designed to take 5 minutes, some of the math has to be easy. Some of the math has to have strategy. And this is part of crisis prevention and critical thinking. Is there a better way to solve a question? If not, let's come back to it later. Guess and move on. Don't leave it blank. If you think this is a question you're going to do at the very end of the exam, guess something. Just in case you don't get to make it back. Because I want you to look at this one versus number 5. Which one do you think is going to be easier and quicker for you to solve? 4 or 5? Without a doubt. 5 takes 20 seconds. 4 takes 5 minutes. You can literally get questions 1, 2, 3, and 5 done and correct in less than half the time that question 4 will have taken you. So in less time, you'll get 80% correct on one passage than you would have doing the one long question. Because note, there's a pattern here. Yes, no. Yes, no. So I want you to think, where in the passage are we going to get some help from? Where in the passage do you think we can get a little bit of help from on this question, according to the question? They can break it down. Yeah, it's pointing us to mechanism 2. Assuming it's correct, is nitric acid a catalyst? And remember, the catalysts aren't used up, right? So we go back and look at the mechanism, or we can even look at the net equation we made for the last one. How do we see if something is a catalyst again on a reaction? Yeah, it starts out as a reactant, but it's regenerated in the end. Now, in that mechanism, what represents nitric acid? Because if you look at the mechanism, be it the net equation we created in number 4 or the mechanism itself, protons. That's going to represent your nitric acid. So you tell me, is nitric acid being regenerated? Is nitric acid being just a catalyst here? And we can see it here in this net equation from question 4. We can see it by looking at the different steps of the mechanism. You know what? It's used up. So we know it's not A, we know it's not B. It's not a catalyst. Therefore, which answer would you select? Which one here is the correct answer? The one that's going to give us all of our points. Is it going to be C because the reaction occurs at the same rate of nitric acid as at present, or D because nitric acid isn't regenerating? It's D. Notice, that's how you approach a question like this. Two parts of the question, guess what? We're going to use both parts to help us narrow it down. Use the easy part to solve, then eliminate based on what you know to be true and actually relate it to the question. So note, 3 easy points, one that was pretty easy, just had to go a little bit longer, and then one that was just going to derail us and slow us down. These are the tenets of the MCAT, specifically of physical sciences. Let's get as many as we can and not worry about the ones just there to slow us down. And so we move in, and note if you want more practice, make sure to go to chapter 12. There are a lot of good high yield problems back there, specifically for finding rate laws. Those are good to practice because you can get faster. Rate law questions aren't necessarily going to take you a long time on test day if you practice and gotten more comfortable with exactly what you're looking for. Other ones, you guys are rocking and rolling. Now that being said, we move into thermodynamics, which is a topic that a lot of students will see and kind of skip over because the questions may take a while. But thermodynamics is really nothing more than the study of a specific state function. Now, state functions are systems that depend solely on initial and final, like enthalpy change. Anytime you're given the enthalpy change, or delta H, your first thought should be, guess what? It's final minus initial. There's a final amount of energy, there's an initial amount of energy, that's the state function. You see the same thing with entropy and Gibbs free energy and delta U. You see the same thing with delta T. Like, let's say that I invite you over to have dinner. And when you come over to have dinner, I tell you, you know what? Well, step one, I heat the water up I heat it up to 52 degrees, but then I cooled it down to 47. But then I heat it up to a boil, but I cooled it down to 87 for a little bit. And then I heated it back up to the boil so I could start cooking. But then I let it go down so it would get cold, and then I started cooking it again. If you come over for dinner, do you really care about a diatribe on how hot and how cold and how hot and how cold I let the water get from time to time? No. You come over for dinner, you want food on the table. That's pretty much it. Right? So that's a state function. Anytime you see that delta Sandia, you know that you're dealing with the final minus the initial. It doesn't care about the path we took. It just matters that we got there. It's like taking a trip. And now enthalpy is one of the big ones. Reactions that increase enthalpy are going to lead to, or are going to be endothermic. If you decrease enthalpy, it's going to be exothermic. So endothermic and exo. If you see endo, think heat's going into the system. And so you can see that your final heat of the products should be much higher than your initial heat of the reactants. So since the final is greater than the initial, your delta H is going to be positive. You're subtracting a smaller number from a larger number. So that's endothermic. There's more heat inside than there was before. So we had to add heat into it. Heat went into it. If it's exothermic, again, you can see the final heat of the products minus the initial heat of the reactants. Here we see the final is less than the initial, so heat had to be lost, which is why delta H is negative. It's going exo, it's exiting the system. It's going exo, exiting the system itself. And so we just have to recognize that whenever a question asks us about change in enthalpy, let's look at our products, let's look at our reactants, and let's subtract the final minus the initial. It's really not too terrible. We're going to get a question like number 6. Now, we see kilojoules per mole, usually a good indication that we're going to be talking about energy per mole, good indication we're talking about enthalpy or heat. But it's asking us about bond enthalpies. So we need to define that before we get too far in. What does it mean to look at a bond enthalpy? Yeah, it's the amount of energy in a bond, right? So bond enthalpy tells you how much energy is in a bond. So now an NH bond has 389 kilojoules per mole of energy within it. It just tells you how much energy it takes to break or make a bond, right? Absolutely. And so note, we can go the traditional route of solving this. The overall change in enthalpy, right, is just going to be input versus output, or the products minus the reactants in a case like this. And so we can look at all the numbers and plug those in. Where the heat of reaction is 1266, where each NH bond is 389 kilojoules per mole, but notice in the balance equation we need to make 4 of them. Then we so we have that. And then note that there are 3 NH bonds per ammonia molecule, so we got to multiply that times 3. Then we have the oxygen-oxygen bond, which is 498, and we make 3 of those. And then we make 2 of the N triple bonds, and then we make 6 of the H2Os, except really in every water there are 2 of them, so we really end up with 12. And we can solve this numerically. Solve for X and we're done. Does this remind you of it? Does this look somewhat familiar to anyone in terms of how you've done enthalpy? Yeah, this is the traditional way of doing it. But I want you to think. We just had a question that took us forever to solve. Do you really think that we're going to have that many questions in our class today that take forever to set up the math and set up? No. The class is just like the MCAT. Sometimes things will take longer. Sometimes there've got to be easier ways. And that's where we defined it. Bond enthalpy is the amount of energy within a bond, correct? Look at these bonds. Which of these bonds has the most energy within it? Which one would you expect should have the most energy within it? Which of these bond enthalpies that they gave us had the most? We would assume that a triple bond should be the strongest, and note that it is. So N triple bond N is 941 kilojoules per mole. We're looking for the OH bond, which is a single bond. Should an OH bond have more energy or less energy than a triple bond? Yeah, it's less. So start eliminating. Triple bonds are stronger, they have more energy. So start eliminating. What can we get rid of just because we know single bonds are weaker than triple bonds? Yeah, get rid of D. Can't be D. So the triple bond should be the strongest, has the most energy. Which one should have the next most energy? Will it be OH? Nope. It's got to be the double bond. Triple is strongest, followed by double. So we could say the O double bond O should be next, and that's 498. Now that doesn't help us narrow it down any further, but we're still making our chart. Then we get to the single bonds. Now it's obviously easy for us to compare number of bonds quickly. Single bonds are weaker than double bonds, are weaker than triple bonds. Triple bonds are the strongest. However, can you compare bond strength when they're the same type of bond? Yeah, absolutely we could. What do you think is going to be the key for us to look at then now in terms of these? And there it is, Dahl and Rashida, yours. It's electronegativity. Oxygen is higher, is more electronegative, which means oxygen has a tighter grasp or tighter grip on the electron. So what do you think that tells you about the bond strength of OH if oxygen has a tighter hold on the electrons? And there it is. It should be stronger than nitrogen. So guess what? You just ordered them. OH should be slightly stronger than nitrogen because nitrogen isn't as electronegative, so it doesn't have as much grip on the electrons. So OH should be somewhere between 389 and 498. Okay, does that help us any? If we know that oxygen or OH needs to be between NH single bond and O double bond O, yeah, guess what? A is too small, B is too small, D is too big, C is just right, there's our match. So note, there are going to be questions that come across as our traditional chemistry, and that's okay. But we can see here, there may be better ways to solve it. So as you go through your homework, especially over the holiday break, but as you go through your homework, I want you to move beyond just looking at questions you get wrong. I want you to start looking at questions that took you a long time and ask as you review, is there a better way? Is there a better way? And that's something that's going to that's going to help you out quite a bit. Now, the O6 question would have been bad to think it was too close to 498. Possibly. OH is going to be a pretty strong bond on its own, right? OO it's going to be stronger, but you don't want to try to guess based solely on numbers. You'll be amazed at how many single bonds are pretty close to double bonds in terms of strength. Single bond's going to be weaker. And part of it, for solids, the reason that single bonds tend to be weaker than double bonds has a lot to do with actual size. So when you're looking at double, single, triple bonds, amount of overlap plays a big role. When you're looking at just single bonds themselves, electronegativity is going to play probably the bigger role than the actual atomic size and how close they get in terms of the MCAT. A nice topic that we can really simplify. Otherwise, we overcomplicate in terms of the MCAT, things like that. So I love what you're thinking. Your thought process works beautifully when it comes to single, double, triple. When it comes to single bonds themselves, it plays some role, but electronegativity differences are probably going to play a slightly larger role. So we can really settle into one definition and make it nicer. Good job. Well done. Now entropy, that's just toward disorder. And note, entropy, again, a state function, and it's usually measured in joules per Kelvin. So you can see that as you change temperature, you might affect your entropy. Fact. Entropy tends to increase with temperature. And if we look at the different phases, gases have the most entropy versus liquids versus solids. No surprises there when we look at the long term, right? Because if we look at entropy in gases and in liquids and in solids, you drop a vial of gas, it goes everywhere. You drop a solid, just pick it up. Things tend toward chaos. And note that entropy kind of matches enthalpy. Like which phase typically has the highest enthalpy or the highest amount of heat transferred into it? Yeah, those gases match this, or phases match this. Gases tend to have more enthalpy than liquids, more enthalpy than solids. Put energy, that's what we do. Put energy in, break the intermolecular forces, go to the next phase. So break the intermolecular forces to make liquids. And we'll talk more about enthalpy and phase changes as we get a little bit deeper. But we got to take our enthalpy change, the change in heat of a reaction, take our entropy change of disorder, put them together with temperature, and we get Gibbs free energy. Delta G equals delta H minus T delta S. You must know this equation. What does Gibbs free energy give us? What does Gibbs free energy specifically give us? If you plug those numbers in and you solve, it gives us what? Spontaneity. Now, I want you to be really careful with your definition of spontaneity. Which direction will delta G tell us about if we plug the numbers in as given on 99.9% of test day? Is it going to talk about the forward or the reverse? Yeah, we're talking about spontaneity moving forward. So G is Gibbs free energy either, and since it's energy in joules, no surprise there. And we can plug in enthalpy and delta S and T. Note T needs to be temperature in Kelvin, so we've got to convert Celsius over. So we take degrees Celsius, add 273, we get Kelvin, just in case we forgot. We're going to plug in Kelvin there. And then remember that this is the complete view. Is it spontaneous moving forward or not? So a negative delta G is spontaneous going forward. You're going to start making more product. It's favored to go forward. Delta G positive means it's non-spontaneous, which means the reverse is actually favored. So delta G tells you the likelihood of spontaneity going forward. If you have a negative delta G, it's going to go forward. If you have a positive delta G, it's going to go in reverse. And if your delta G equals 0, then we know we're at a nice, healthy, steady equilibrium, which is definitely something that most reactions aim to attain. We can see that working out for us here. So we've got a couple of critical thinking questions to ask us. Let's dig a little bit deeper into Gibbs free energy. So this one wants to describe the system at a low temperature. And note you have a positive delta H and a positive delta S. So if you have a low temperature, is this going to be spontaneous or not? Spontaneous. Now, before we dig too deep into it, how many of you remember making charts like this, where you looked at delta H and you looked at delta S, and you asked yourself if this one's negative and positive, and this one's positive and negative, or if they're both positive, or if they're both negative? How many of you remember setting those charts up back in college or even maybe in high school? Oh, yeah. And the chart's actually not a bad thing to have in your back pocket. But the chart comes from that equation of delta G equals delta H minus delta T, or minus T delta S. We have two groups. We have what we consider temperature independent, so it doesn't matter what the temperature is, it'll either always be spontaneous or not. And then we have the two sets that are temperature dependent. When temperature changes, that will affect the reaction. So note, if you have the same sign, like we do here, that's temperature dependent. Now, if delta H is negative and delta S is positive, that's always spontaneous because you're always going to end up with a negative number. In reverse, you're always going to end up with a positive number as you take a positive and subtract from it. What kind of temperature will you need, though, if they're both positive and you want it to be spontaneous? If you want that second term to cancel out the first term, you need a high temperature or a low temperature to make the second positive term cancel out the first positive term. Yeah, it's spontaneous if you have a high temperature. Because note, you're going to be taking a positive delta H, a positive T. Remember, the lowest possible value of temperature, 0. That's why we do this in Kelvin. And so if you have a positive delta S and you try to subtract, you need a bigger second number than a first number. And therefore, if it's spontaneous at high temperatures when they're both positive, it's going to be spontaneous at low temperatures when they're both negative. We can plug numbers in and see that as well. So here, low temperature. Is it going to be spontaneous or not spontaneous if they're both positive? Yep, here it's not spontaneous. So what phase are we going to see this reaction remaining in if it's not spontaneous? Because now all we see is we have XL to XG. It's not spontaneous here, so guess what? It's going to end up staying the liquid form. So how are we going to eventually turn this liquid into a gas? What are we going to do to make that liquid start boiling? Well, guess what? We add some heat to it. We break those intermolecular reactions and we start going. So if we increase temperature, if we go from a low temperature then to a higher temperature, you'll note, now we can move to the gaseous phase, as long as the temperature gets high enough. As long as the temperature gets high enough. So at a low temperature, it's going to be a liquid. At a high temperature, it's going to be a gas. And there must be some temperature where the liquid becomes a gas. What do we call that temperature? When we're asking about where the liquid becomes a gas. Yeah, that's just our boiling point. And that's what question 3 is asking. What is the temperature at equilibrium? So, think step. We got to translate. What does it mean to be at equilibrium? Thinking about the information they've given us. There it is. Delta G has to equal 0. So we can set up the reaction. The forward and reverse rates are equal, therefore delta G is 0. It's going forward and reverse at the exact same rate. And we can plug in our delta H, we can plug in our S, and we can get our T. Now, there's one thing you may notice about this question that if you just start setting it up, you're going to have trouble. Like, a lot of students will start setting up, we'll have 44 minus T times 118. And the problem is, that's going to give you a wrong answer. Why? I mean, delta G is delta H minus T delta S. And there it is. Swati, yeah, you know what? Units. MCAT makes sure you're paying attention to units. MCAT makes sure that as med students, we pay attention to the details. As doctors, we're going to realize the importance of not just rushing through it. So we've got to make sure to convert. So in reality, we have 44,000 joules. And if we solve for temperature, it's 373 Kelvin or 100 degrees Celsius. So the last question asks us to determine what is this mystery substance by which we have encountered? What is this mystery substance that goes from gas to liquid at 373 Kelvin or at 100 degrees Celsius? And there it is. It's got to be water. Because we know the boiling point of water. That's it, point blank. So note, right? Note, is the MCAT going to require us to memorize a bunch of random boiling points? No. Water tends to be the one constant that we've got to know things about. Boiling point of water, 100 degrees Celsius. Freezing point of water, 0 degrees Celsius and things like that. And being able to convert over as well. Right? Keep that in mind. Now let's do another critical thinking exercise. And I like this exercise. It ties back definitions from Chemistry 1 to remind us that sometimes when we can keep it basic, we're going to get a lot more points from it. Now, delta H5 has a special term. You're going to take sodium in its natural state chlorine gas in its natural state and make sodium chloride. Therefore, we call this the heat of formation of sodium chloride, or delta H naught, or rather super naught sub F. Standard heat of formation, right? Standard heat of formation. And to define it, standard heat of formation is nothing more than the enthalpy change required to make a molecule from elements in their standard state. So all delta H5 tells us is the amount of energy it took to make sodium chloride from elements in standard state. And we remember that chlorine is normally found as one of our Hofbrinkel diatomic, and we know it's a gas. Sodium is usually found elementally as a solid on its own. Its natural elemental state. Do you need to memorize a bunch of standard heats of formations? No. But if you see this term, you do need to recognize what it stands for. Because questions may require you to use something like this. What is the standard heat of formation of O2 gas? You tell me. How much energy does it take to make O2 gas from elements in their standard state? Well, guess what? It's zero. Why? And there is, because it's in elemental form. It's in its standard state. So if you go back to your reading, you'll note there are some standard states listed in the chapters you read for today. Most of them we've already talked about, like your Hofbrinkel gases, sodium. You're not expected to remember the standard state of most of the elements. Usually it's just going to be the element itself. Sometimes it may be diatomic, but there are some the MCAT expects you to realize this is how they're found in nature. O2 is naturally found as a diatomic molecule, and it's found as a gas. So note, any element in its normal state requires no energy to make it. Think of it this way. The Earth has already made this element to look like this. It's not going to take any extra energy for me to do that either. So we have the standard state right there. Now, delta H1. Notice we're going from solid to gas. What would you call that? If you're going from solid to gas, what would you call that heat? Heat of what? Yeah, and Ruth, Lauren, Ruth, Michael. Yeah, that's heat of sublimation. And note, it's going to be endothermic. You have to add heat to make the solid become a gas. We can think about trying to vaporize an ice cube. Got to add some heat to it. Then we look at the next one, H2. We go from solid, so we go from gaseous sodium to ionized sodium. We're removing an electron. What is that amount of energy called when you're adding energy to yank an electron off? This goes back to Gen Chem 1. There's heat of ionization energy, absolutely. And note, this is also endothermic. I have to add energy to yank off an electron. Doesn't matter that sodium's ready to give up that electron, it's still going to take a little bit of energy for me to yank it off. So that's what that is, ionization energy. So note, delta H1 and 2 are both endothermic. We're going to have to add energy to get solid sodium to the gaseous ionized form. Now, delta H3 is going to be what we consider half the bond enthalpy of chlorine gas. Because we're taking chlorine gas, we're splitting it in half, and we're leaving with chlorine. And again, that's endothermic. Bond breaking is endothermic. Bond making is exothermic. So when you break a bond, that's going to be endothermic because you're disrupting it. There's one exception to this rule, though, about bond breaking and bond making that the MCAT will expect you to realize on the top of your head. What is the one biological molecule in which breaking a bond is not endothermic? And we talked a little bit about it before, but Christine, Tay, Kimberly, it's ATP. In almost every molecule you're going to encounter on your MCAT, breaking a bond is endothermic because you're taking you're taking elements with happy octets and snapping them in half. ATP, though, not the same. ATP loses that fast phosphate, and that's actually exothermic. It releases energy to make that. So exception being ATP. So breaking is endo, making is exo, with the exception of ATP. Now, what are we going to call delta H4 when chlorine gas adds an electron? What are we going to call delta H4 when chlorine adds an electron? What is that amount of energy called? Thinking back toward, again, Gen Chem 1. Thinking back again toward Gen Chem 1. There's electron affinity, absolutely. When we look at an element in gaseous form, add an electron, we just call that its electron affinity. And now this is going to be our very first exothermic process in this mechanism because chlorine wants to gain the electron. Why is it going to be an exothermic? Why is it going to release energy when you take chlorine and add an electron to it? Why is that favorable? Because no, ionization energy, energy to remove an electron. Electron affinity, energy released when you gain an electron. Ionization is a process of making ions. Ionization energy versus electron affinity, though, will be very different ions that are going to be made. So don't get ionization and ionization energy confused. They're two different entities in terms of general. And there it is. Give an electron to chlorine, you get a happy, healthy, stable chlorine atom. It's got its nice octet, it's happy, it's good. It's better to have it there than on its own. That's exactly what we see. So no, we've got our exothermic process. Now, if we look at delta H6, do you think it's going to be exothermic or endothermic? When you take ionized gaseous sodium, ionized gaseous chlorine, and make solid sodium chloride. And there it is. It's going to be exothermic, without a shadow of a doubt. You're taking gases and making a solid. Remember, if you're trying to freeze something, right, you would take it, throw it in the freezer. You're removing the energy from it. Energy is going to be released. So it's exothermic to do that. Now, Hess's law, you may recall, says that it doesn't matter the pathway, every reaction will take the same enthalpy change. So the total change in enthalpy will be equal to each individual step. So delta H5 is the shortcut. But delta H5 will equal H1 plus H2 plus H3 plus H4 plus H6. Doesn't matter the pathway, you're going to see the same change in enthalpy overall. Why? Because enthalpy change is nothing more than final minus initial. If there are a lot of steps, you can add them all up and get the overall difference. That's Hess's law. What about entropy? How is entropy going to be affected in this particular reaction? You think it's going to increase or decrease as you go from solid sodium and gaseous chlorine to solid sodium chloride? And Michael, yeah, guess what? You're putting things together. It's going to become more order. So in fact, it's negative. We get more order. We're going from 1.5 moles to 1 mole. We're going from gas to solid. We're adding order. Now, we know that we know that entropy in the universe is always going toward disorder. That's total entropy in the universe. But in individualized reactions, you could tend toward more order. It just turns out that if you take all the processes in the universe at any given point and add them together, all the processes in the universe are going to lead to continued more disorder. But there are going to be ordered processes in there that you add as well. Nature seeks that chaos. There you go. Now, one last piece of the puzzle before we go on to our second passage. I want you to look at this. The delta H of the reaction. This is your generic form. This just means that you're looking at the change in heat of a reaction itself. What do you think it means then if I say something like delta H redox? What do you think that would mean if I said that instead? Okay, well, there it is. Delta H of a reaction is generic. It could be any reaction. It's just a reaction you're looking at. Sometimes the MCAT likes to specify. So this would be for a redox reaction, right? Or delta H neut might be for a neutralization reaction. So this is one of the things that drives a lot of us crazy in Gen Chem. There always seem to be 75 names for the exact same process. The only thing general chemists do is they use the subscripts to specify. So when you see delta H, it's going to be the same thing either way. Doesn't matter. Delta H is is going to be the enthalpy change of a reaction. The subscript just means the specialized type of reaction. So if you see delta H in some subscript, all you know is the type of reaction you're dealing with. Because if you look at the next passage, you're going to see, if you do a quick preview, that there is a weird looking delta H here. And it's got subscript. So what kind of enthalpy change, what kind of reactions do you think this passage is going to be talking about, since the MCAT is using one of Gen Chem's specialized types of enthalpy changes? And there it is. We're going to be talking about either combination or combustion, right? Here it's going to be a combustion reaction. But we have a pretty good guess, and as we read further, we're going to know everything we need to know about it, which is good. So what I want you to do is we're going to do this a little bit different. Up until this point, we've been road mapping on our own, reviewing our roadmaps, and then going through the questions together. I want you to try passage 2 on your own. So I'm going to give you 7 minutes to map and to attempt the questions. Now, does that mean in 7 minutes you should be able to answer every last question and get every question right? No. What should you do in this time frame? What is the key component that you should be aiming for in these 7 minutes? 1, get a roadmap. 2, triage the questions. And 3, if you're triaging and trying to get the easy ones versus the harder ones, 3, get as many done as possible as you can using the methodology. You may not get every question correct, and that's okay. On test day, we don't need every question correct to get a top-notch score that gets us into med school. But we do have to be able to get to every question and recognize when some are going to be wasteful. You're going to notice in this particular passage set, there are some wasteful questions. So take 7 minutes, read through passage 2, map passage 2, try the questions, make sure to stop, think, predict, and match, and then attempt questions in the order where you go for the easiest ones first, say the hardest, longest ones for later. We'll talk about the answers. Okay, team. So let's do a little review. And note that our TAs have put a passage map up there for us. Our nice little informational passage on enthalpy. We see lots of enthalpy, lots of combustion, lots of tables, lots of data, lots of graphs. But I want you to think about this. If you haven't had a chance yet, feel free to put your answers into the polls as I bring them back up. I want you all getting a chance to test these out. But what I want us to think about and utilize right now is actually, I want us to think about triaging. Number 7. Number 7, in fact. Is number 7 a good question for now or for later? Yeah. This is the one to do absolutely last. This is the question that's designed to slow us down if we're not incredibly careful with it. And in fact, if we look at it, it's all about the setup. Notice heat of formation of CO2, heat of formation of H2O. We need the heat of formation of acetylene. What info did the passage give us about acetylene that we'd be able to use in terms of delta H? Because this is probably the one, this is without a doubt the one I would guess on and come back to at the very, 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 very end. And it gave us heat of combustion. It gave us overall enthalpy change. So here, note, we need a balanced equation and we need Hess's law. Now, it's important to remember that combustion means carbon source in the presence of oxygen yields carbon dioxide and H2O. So we're going to take our carbon source, acetylene, we're going to put it with some O2, and we're going to make CO2 and H2O. That's combustion, but it's not balanced. So we've got to balance it. Now that we've balanced it, we can actually do our enthalpy change overall using Hess's law, right? Remember, the enthalpy change is the enthalpy in the products, that's our final enthalpy, minus the reactants, or our initial enthalpy. And so here we start plugging it in. Since we're combusting, we're going to look at the amount of energy in CO2 and the amount of energy in H2O minus the amount of energy in acetylene plus H of energy in O2. And we start plugging those numbers in. Does this question look like it's getting any faster as we put more and more into it? Not really. Not really. If we finally do the math, no, we can estimate a little bit easier. Negative 1255.5, that's going to be closer to negative 1300. Negative 393.5, let's call it negative 200. Negative 241.5, let's call it negative 250. Because note, these answer choices are pretty far apart from each other. So the farther apart your answers are, the more liberal you can be with your estimating. Make your math easier. Make everything end with zeros. Because when you do all this math, you're going to find out that acetylene should equal 250, and that's going to be closest to answer choice C. But we may have gotten this one wrong. Is that okay? Is it okay if we get this question wrong on testing? Honestly, yeah. When is it okay to get this question wrong? Why is it okay, I should say, to get this question wrong? Because there is. You're going to spend 5-6 minutes doing this. How many other questions could you get in that time frame? Well, guess what? There are at least 3 other questions that combined will take less time than this one. It's all about using our time effectively. And note, when you get a question like this, the tendency is to rush. When you have a lot of math, the more you rush, the easier it is to make a mistake. This took a lot of interpretation. That's okay. Questions on tests, they can do that. But we're not going to spend our time doing this if there are other easier, better, faster questions ahead of us. So you know what? We guess, move on, and come back if we need to. Also note, if you tried this one, it's good to review and see what you messed up on. Things that you mess up on during time tests are things that you traditionally mess up on the actual MCAT. So if we note here that we forgot to balance, or we forgot to think about combustion, or if we plugged the numbers in wrong, or we estimated wrong, or we forgot to carry a negative, these are good things to note for later, because those are things that we can work on and fix and perfect. Little things now mean big points later, things that we may forget to do from time to time. Like I used to always miss negative signs. You guys have even seen that, I think, occasionally when I forget to put a negative sign and catch it when we're going through class. The more we do it, the more we catch it, the better we're going to be on test day. Number 8, though, let's face it, number 8 is a much easier question. Which of the following will produce the greatest increase in entropy? And note, everything's combustion. So what should we be paying attention to if we want to find the most disorder of all? We can go to the table, and since it's combustion, we're going to do a little bit of size. What are each of these products going to make again? If we're combusting these carbon-based sources, well, we're going to make carbon dioxide and water. That's what combustion does. Now note, almost everyone eliminated B and C. Why? Those are the exact two you should eliminate, not even pay attention to them. Strategically, though, I want you to tell me why. Why is it good to eliminate those two? And they're in the middle. If we want the greatest, then we're going to want the thing that's smallest or the thing that's largest. And it turns out you guys are saying it's glucose, and you're exactly right here. It is going to be combustion of glucose overall. High entropy means more disorder, and remember, the more molecules you get, the more disorder there's going to be. So the more we can make, the more disorder we get, and glucose is going to make a whole lot more CO2 than hydrogen ever will. More carbons means more CO2 means good stuff. And also note you can also use, and you think about the phases as well, gas versus liquid versus solid. Now, more, if you're asking about reacting, that's good. Note that since we're looking at the combustion, we're going to primarily think about the products that we're making because it's asking us which reaction would produce. Which reaction would produce the most on testing. So that's good. We're really paying attention to just the products here from this question. That's enough, my friends. Now, number 9. Number 9. How many of you went to number 9, skipped it, and came back a little bit later? And Chelsea, enthalpy and entropy themselves are independent pieces. So enthalpy is the amount of heat transfer, entropy is the amount of disorder. Put those together for delta G. Although they tend to have similar trends. Gases tend to have more enthalpy and have more entropy, but they are two separate pieces, although temperature has something to do with it. And so could you have used the relationship from the equation? If you knew the enthalpy changes and the heat of reaction things, you could plug those in and solve it. Although that would take you a lot longer time because the more math you do, the longer it's going to take. One thing I want you guys looking for is there a relationship way versus just the plug and chug way? That's a good question. Number 9, though, we're going to need to plug and chug. And this may be one you came back to. But note the passage even gave us the choice, even gave us the equation to use. So given that the S for combustion is 0.217 and the temperature is 295 degrees Celsius, but we've got to remember we can't use Celsius. We've got to convert to Kelvin. We want delta G and we need delta H. So we go back to the table and we get the delta H for ethanol, which is what? Negative 1235.5, something like that. 1235, yeah. 1235.4. So make sure I got the exact 1235.4. And then we subtract that out. And we can plug our numbers in and solve this. However, I want you to look at these answer choices. We could totally round and do the math and find it. But before you round and do the math, I want you to take a quick look. We don't have to do any math before we're done. Because note, we have a negative number, negative 1235.4, and we're going to subtract something from it. So what can you tell me about delta G if you subtract from a negative number? It's got to be more negative. You're going to end up with a much smaller number. It's going to end up being more negative. Remember, the more negative something is, the smaller the number it is. But if you're subtracting from a negative number, you're going to make it smaller. So guess what? It's got to be D. At that point, we're done. No reason for us to do a single bit of math once we did that setup. So if you had done the math, estimating it, absolutely. But one thing I want to ask you to do and think about is, do I even have to do the math for that one? Now, A is a bit of a trap if you forget to convert over from Celsius to Kelvins. But again, mistakes today means points tomorrow. Win-win. It's good to make them now. Make them now, don't make them later. But that's what we've got to review. See what our mistakes are so we can fix them before we see them. And no, because you could have gotten rid of C right away. You knew you were going to do something to 1235 exactly right. Once we knew we were going to make it smaller, we also got rid of A and B. Love it. Nice strategy. You make the same. You did the same thing I typically do in math. Occasionally, if I'm rushing, I miss a negative. Number 10, though, you guys handle beautifully. What have we talked about tonight that helped you with number 10 when you're thinking about solving this one? We want the temperature dependent. We think about the chart we discussed earlier, remembering that when the signs are the same, temperature is going to matter. So in a question like this, you could start with the piece that's easiest and start eliminating. We know that temperature dependency requires the same sign overall. So guess what? 1 would matter. Since 1 matters, it can't be D. Then we know that 4 should matter. And if we look at 4 and know that they're both negative, at that point, we're done. Same signs. And note, this is just a restatement of that chart. Same sign, temperature dependent, different signs, never temperature dependent. And we saw that as we plugged in numbers. But after class, I want you to review this passage and think and try these questions and ask, what did I do that may have cost me some points? Looking for those things now means that we can fix them. Test A problem number 1 has nothing to do with content. It tends to do with rushing, forgetting, and missing something in the critical thinking. The more we recognize what we miss, the sooner we can overcome it, and the easier it's going to be that MCAT expert that we need. So make sure to review these questions and the explanations to get more sense of what you can do. Just that is a good start after class to get some more practice with methodology, practice your reading, practice your passage mapping, practice your strategies, and things like that. So no, equilibrium, the whole thing. I want you to think of it this way. How many of you can remember as a kid going on road trips? Like getting in the car and just driving, countless hours away, sitting in the back saying something along the lines of, are we there yet? 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 Dalton, you and I right now are literally insane. Well, you still do. Long road trips can be awesome. Sometimes they tend to be long. So reactions are very similar to us in that as you take a trip, you want to get to your destination. Reactions want to get to their destination as well. Their hotel, their pool, their lounge, that's their equilibrium. So reactions are constantly trying to get there, with the reactions and products asking, are we there yet? So when it gets there, it's nice and happy. And when we get to equilibrium, we know that the rate moving forward equals rate reverse, and as we talked about earlier, delta G equals 0. However, just like a road trip, you're not always going to be at the hotel relaxing. Sometimes you're driving toward it, sometimes you went too far and had to turn around and go back. And so when we're looking at a reaction, it's important to remember that capital K equilibrium is always just going to be the concentration of products over the concentration of reactants at equilibrium. So this is a very specific ratio for your reaction. Your reaction will tend toward this. If it's not there, it's going to keep going. Are we there yet? And so to determine whether or not you are there, you look at the reaction quotient. Equilibrium constant is where you're going. Reaction quotient is where you are now. Are you a few hours away? Did you accidentally drive past the hotel? Any of you have ever been to Louisville, Kentucky, you'll know that it's very easy to somehow drive past the city and end up in Ohio. Crazy, right? Anyway, that's one of the road trips I remember as a kid. And so no, the Q changes until you reach that equilibrium constant. So Q is where you are now. Equilibrium constant, where are you going? And so Q is always trying to reach KQ. The trip wants to be over. We want to be in the hotel. We want to be sitting by the pool. We want to be relaxing. But we got to get there first. We got to get there first. And so remember that since it's where we're going, it's just that relationship, products to reactants. And when we set that reaction up, remember, as we talked about in our polls at the beginning, we only include the gases and the aqueous phases. No pure solids, no pure liquids, boot them out, right? Now, equilibrium constant, or rather the reaction quotient, is the same thing. Q is just going to be products over reactants as well. Remember, it's just products over reactants right now. Equilibrium constant, that's that ratio at equilibrium. So you can compare your product to reactant ratio now to where it should go and determine, do I need more product, do I need more reactant, or am I just right, like Goldilocks? And so we want to look at those situations and think what needs to happen. So let's say Q is too low. There are two things you can do to make Q bigger. What are the two things you can do to increase your reaction quotient or make it larger where you are exactly right now? What are the two things you could do to make Q bigger? One is you can increase your concentration of product, right? Increase your numerator, increase your number. The other thing you can do is decrease your reactants. Since it's in the denominator, it's inversely related. So if I need to increase my Q, those are the two things I can do. Which direction then is your reaction going to go to increase product and decrease reactant? Which way can your reaction shift to make that happen? Is it going to go forward or reverse, right or left? I know forward, right, forward, right, forward, right. There it is. So if Q is too low, you're not at equilibrium. You're going to go forward. You're not there yet. Now, when it equals equilibrium, then you're there, then you're happy, everyone's rocking, everyone's rolling, everyone's comfortable. Occasionally, though, as we said, your Q may be too high. So we'll need to lower it. What are the two things you can do to make your reaction quotient smaller, as it will need to decrease to get to equilibrium? How can you make that Q smaller? How can you make that number lower overall? And again, note, we use our equation, products over reactants. So you can either decrease the numerator since they're directly proportional, so decrease product, or you can increase your denominator since they're inversely proportional, increase reactant. So which way should this reaction go now? If Q is greater than KQ, if you went too far, if you missed the exit in Louisville and you ended up in Ohio, so now you got to circle around and figure out how to get back to Kentucky. Now you go in reverse. Now you go backward. Now you go left. We accidentally missed the turn. That's okay. That's what the road is for. Make a circle on the next exit, go back, get to the hotel. Everyone's happy. So that's what Q tells you. Are you there yet? And if not, you can look at your Q value and determine, am I going to move forward or am I going to move in reverse? And you can find Q by taking your products, dividing by your concentration of reactants, and compare, am I at that constant? That's all Q tells you. Now, we just rationalized, believe it or not, you guys just rationalized. You guys just created, basically, the equation on page 193. Now, this equation, does this look like a fun equation to use on testing? No. Not at all. However, this equation relates spontaneity, Q, and KQ. Now note, R again is the universal gas constant in joules per mole Kelvin. T is the temperature again in Kelvin. Q is your reaction quotient. KQ is your equilibrium constant. Question. Is the MCAT really going to ask you to find the natural logarithm of something and find it mathematically to go back and solve delta T? So it's time for a little bit of conceptualizing logarithms, be it a natural log or a normal log. Be it a natural log or a normal log. I want to give you a shortcut to make your life a whole lot easier on testing. If you are taking the logarithm of a number that is a decimal, meaning that it is less than 1, so some number between 0 and 1, it will always be negative. If you take the log of a whole number, which just means it's greater than 1, it will always be positive. Always. So I want you to think about this. Real gas constant is not going to be positive. It's 0.08. We know that's a constant we have to know for testing. We talked about that in Gen Chem 1. It's one of the few constants they actually expect us to remember, 0.02 or 0.0821. Temperature, since it's in Kelvin, is also going to be positive. So that logarithm is going to tell you if it's spontaneous or not. So let's say that Q is in fact less than KEQ. Let's say that Q is in fact less than KEQ. Are you going to have a whole number or a decimal as your logarithm? Yeah, guess what? It's going to be a decimal because you're taking a smaller number and dividing it by a larger number. So if you take the log of that Q divided by KEQ, should you get a positive or a negative? You get a negative. What does that tell you about your delta G then? If I throw a negative in here, guess what? My delta G is negative, so it's going to be spontaneous. Which direction, again, is it spontaneous with delta G? It's spontaneous moving to the right, moving forward. Didn't we predict that just a few seconds ago? That if Q was too small, that it should move forward, that we need to make more product? Sure did. All this equation is doing is codifying the good work you already did. So if Q is too small, you get a negative logarithm, therefore you get a negative delta G, therefore it's spontaneous. Ta-da! If Q is too big, then you have a whole number, then you get a positive delta G, and therefore it's not spontaneous. That's exactly what you guys just predicted on the last page. It's just here in mathematical form. Logarithmic tricks are one of the best things about the MCAT because it's incredibly rare that we see them. Now, the second equation is slightly different. You'll notice that here, we're not talking about just delta or Gibbs free energy. We're talking about standard Gibbs free energy. What that small super knot is indicating is that we're dealing with standard conditions, not STP, standard conditions. And in standard conditions, we assume we're at 25 degrees Celsius at 1 atmosphere and at 1 molar concentration for every reactant in every product. So what this second equation is going to show us is based on your KEQ, is this likely to be a spontaneous reaction? So note, again, we think about our logarithm. Let's say that at equilibrium, your concentration of products is considerably larger than your concentration of reactants. Should you have a big Ka or a small Ka? Remember, KQ, same thing as Q. You end up with just concentration of product over reactant. So if you have a lot more product than reactant, you have a big number on top and a small number on bottom, should you get a big KQ or a small KQ? At equilibrium, Osei, Caleb, Esther, Dalton, Bedore, yeah, you get a big KQ. Notice, your big KQ going to be greater than 1. So what will the logarithm of this KQ be if it's big? Yeah, you should get a positive logarithm. So according to this equation, what will your delta G sub naught or your super naught be with a positive KQ, given that R is positive, T is temperature in Kelvin, so it's positive, and logarithm is positive. Therefore, notice, don't forget the negative sign here. It's easy to speed through and not see it and end up making a mistake. What's your delta G going to be here? Delta G is going to be negative, so notice it's going to be spontaneous. So what the second equation does is, the first equation helps you determine if your reaction is going to be spontaneous from this point. The second equation tells you whether it'll be spontaneous under normal standard conditions. So when you're given an equilibrium constant, it just gives you an idea of, do I make more product or more reactant? If I need more product, likely to go forward. If I need more reactant, likely to go in reverse. So that's what the second equation gives you over the first. The first one, let's look at the reaction right now. 2, let's look at the reaction that's yet to undergo under standard conditions and predict. Do we think it's going to be spontaneous or not? Nicely done. So you tell me, what does this mean in terms of delta G for this reaction if Q is less than KQ? Noting that this is pretty close to what we just discussed. It's just right hand in hand with all of our newfound love of equilibria. Well, if we have a fraction between 0 and 1, we think back to our equation. We remember that the logarithm of a number between 0 and 1 is negative, which means we end up with a positive r and a positive t and a negative logarithm. Therefore, we get a negative delta g, and therefore it's going to be spontaneous. And that's exactly how the MCAT expects you to use those equations. Recognizing that Q and KQ are nothing more than ratios, and if you have the ratio of product to reactant, you can determine whether it should go forward or should go in reverse, or under standard conditions, what's likely to happen. That's all this question here is trying to put out. But you know what? This is, in fact, going to, since we're not at equilibrium, it's going to keep going forward, because we know that if delta G is negative, it's got to be spontaneous. It's going to keep moving forward, going to keep going on that way until we get it down. That's equilibrium. Now, let's say most of you are probably home right now on Christmas holiday from college. Not everyone, but some of you are. Let's say that your physics professor calls your house tomorrow and says, hey, I can't find your physics final exam. You got to get it to me today by 5 p.m. or I'm going to fail you in class. What do? That's like the world's worst nightmare. Like, I graduated from college in 2004, and I still have that nightmare now. You panic, you cry, you get nervous, and then guess what? You figure a way to get it done. You get it done the best of you can, and you hope for the best. When life throws stress at people, all we do is take the stress and try to take it in stride. All right? We find some way to fix it. Le Chatelier is honestly nothing more than, let's take this happy, healthy equilibrium and let's stress it out. See what happens. And so there are 3 ways that you can stress a system. I want you all to tell me, name one of the 3 things that Le Chatelier does to stress the system at equilibrium and watch its reaction to re-equilibrate. It has that moment of fear, it gets its work done, and then it gets back to its life. One thing, we can change concentration. Add a product, add a reactant, remove a product, remove a reactant. That's usually the one that's most straightforward. Second thing, we can change pressure. And third, we can change temperature. So the 3 stressors the MCAT's going to depend on. Now, changing concentration and pressure, those are going to affect our value of reaction quotient. Because if you change the concentration, you change the concentration right now, but it's going to go back to equilibrium. If you change the pressure, you're going to change the concentration of something right now. But temperature, no. Temperature affects KQ. What? Because think about it. Temperature affects the rate law itself. Because you guys remember this. How many of you remember a time where you would be sitting in Gen Chem lab and your professor would say, you know what, well, this reaction is going to take 5 hours and you can't leave till it's done, but I'm going to go home and eat dinner. If you have questions, ask me tomorrow. Do any of you have a chem experience along those lines from lab? I did. My professor would give us 7-hour labs all the time and then go home. So what did intrepid young Mr. Brooks here do when professor was out the door so that this reaction would not take 7 hours, but instead could be done in 30 minutes so I could go home and eat as well? I would grab the Bunsen burner, I would set it on, and I'd turn it up. Adding temperature usually speeds things up. Now, it turns out that occasionally, when I did that, it actually did the worst thing I wanted it to do. But adding heat will affect the reaction itself. So since you're changing the rate, you're affecting KQ. So note, these are the 3 stressors. We're either going to change Q and readapt, or we're going to move the KQ so that the entire relation has to adapt as well. And these are usually things that we tend to feel most comfortable with, which is good. We want to be aware of how to use them. So for any reaction, if I want to shift it to the right, I can add reactant. If I want to shift it to the left, I remove reactant. If I want to shift it to the right, remove product. If I want to shift it to the left, add product. Makes sense. If I add product, I'm going to get more reactant. If I add reactant, I'm going to get more product. Add it on one side, shift it to the other. Remove it on one side, shift it to that same side. So for any reaction, concentration plays a role. Now, do you think the MCAT's going to ask us primarily about concentrations that straightforwardly? Probably not. Mostly because that's the one students tend to be the most comfortable with. That's okay though. It's good to know strategy. Concentration shows up in a lot of different ways, but it's usually the most straightforward. So when we see it, we're going to feel good, we're going to feel comfortable, we're going to feel confident about it. That's what I want you guys to realize. So KQ more, that depends on rates. Concentration doesn't affect the overall rate law itself. Temperature does, because temperature affects your rate constant. So concentration won't affect your KQ. If you add something, it's going to go back to the same KQ you had before. That constant ratio depends on the reaction and the temperature it's at, not the concentration of the products. So concentration won't affect your KQ. It just affects where you are now, not what equilibrium is. Since your concentration doesn't affect the actual reaction itself. It just allows more of one thing. Now for exothermic and endothermic, right, and more, Le Chatelier's for equilibrium. You have a system in equilibrium, you add something to it, and you say, watch it readapt back to equilibrium. So Le Chatelier only applies to systems that are already at equilibrium, and the stressors you add to shift it back or forth to get the rate law forward equaling the rate law in reverse. That's what Le Chatelier is going to be. Now, exothermic and endothermic, what do you think is the easiest thing for us to tether exothermicity and endothermicity to in terms of a reaction? Yeah, and Ose, Lauren, heat, delta H. Look at enthalpy. So what do you think about? Think about an endothermic reaction where heat has to be added. If I add heat to my reaction, is heat more likely a product or reactant if I'm adding it to my reaction? Yeah, heat's a reactant. So in endothermic processes, think of heat as a reactant. You have to add it to make the reaction go forward. If it's exo, you know heat's exiting, heat's released. And if heat exits, you can think of heat as a product. So instead of us looking at temperature and heat changes in their own unique light, we're just going to ask ourselves, you know what, is enthalpy a reactant or a product here? And then think about temperature changes as adding or removing heat or product. If I want to shift it right, do I add or remove product? If I want to shift a reaction to the product side, do I add or remove product? If I want to shift it to the product side, do I add or remove product? Yeah, if I want to go to the product side, I need to remove product, right? Add product, go reactant. Remove product, go product. Add, go to the other side. Remove, go to that side. So if I want to make it go to the right in an exothermic process, I need to remove heat, decrease the temperature, remove that product. If I want to shift to the reactant, I add heat, add product. Add, go to the other side, remove, go to this side. Exactly right, Rashida. Go with where you lack. And so an endothermic process will be the exact opposite. If the heat's a reactant, we add heat, go to the product side. If heat's a reactant, remove heat, go to the reactant side. But whenever it talks about forward, it's talking just about the product side. It's going reactant, that's going to be going to the left or going to the reverse. Now, we already said this before. When it comes to equilibria, we only care about gases and aqueous phases. When it comes to pressure, that's only going to affect one phase. What phase does pressure affect? And it only affects gas. So when we're looking at pressure, we only care about number of gas moles, nothing else. If you increase your pressure, you go to the side with less gas. If you decrease your pressure, you always go to the side with more gas. And note, sometimes they may give you volume instead. So we have to remember that volume is inversely proportional. So lower the volume, increase pressure, go to the side with more gas. Increase volume, decrease pressure, go to the side with more gas. So less or more, right? Increase pressure, less gas. Decrease pressure, more gas. Give the gas room to run. So if we decrease the number of gas moles, that means that we can increase pressure to go to the right because there are fewer gases in the product than in the reactant. or vice versa to go to the left. If we increase the number of moles of gas, that means that we're going to have more gas in our product than in our reactant. And if there's more gas in our product, to get to our product, we need to decrease pressure to go to the solid. More gas, and we need to increase pressure to go to the solid. Less gas. So this is a Le Chatelier principle chart, and this is a good one to dog ear and look back at later. But is it enough? I want you to think from a study perspective, from an MCAT perspective, from our future medical student perspective. Is it enough that we just memorize this chart for testing? Nope. It's in the usage that it makes most sense. And that's exactly what we're going to be moving to next. We've got to be able to explain it. So this chart may feel a bit obtuse. It's a good one to review, but it's in the usage that all these rules are going to make a little bit more sense to us. So we have three systems that we can apply these rules to get a better sense of how to use them. Now, question one has to do with setting up the equilibrium constant itself. What's our generic form for an equilibrium constant? We're going to go set an equilibrium constant up. What's our generic equilibrium constant format? What goes on top, what goes on bottom of this? There it is. It's always product concentration over reactant. So here, it's not going to be a big deal. What's our equilibrium constant? Well, just plug it in. Our products are going to be NO2 squared. Our reactants here are going to be N2O2. And note that both our product and our reactant are gases, so we can include them both. That's step one. That's your KEQ. We just have to find our product, our reactant, and use our balance equation. Remembering that your balance coefficient becomes the exponent for your ratio in the equilibrium constant, or even in cubes. So step one wasn't too terrible. Set up our equilibrium constant. Now question two, does this look like a question for now or later? When it's asking us, given this equilibrium constant, what's the concentration of NO2? This is a later question. However, most of you probably remember setting things up like this with ice tables. How many of you remember the ice table? Yeah, briefly. If you don't remember ice tables, I don't want you to worry about it. Ice tables are a bit convoluted. We're going to modify that into a nice three-step method to make the most of this. So if you don't remember the ice table, I don't want you to ever go look at it again. There's a better way on testing. And we're going to approach it right now. So we need to find we want to find how much NO2 there is. Now, before we can do anything, we need our equilibrium constant, which we know is NO2 squared divided by N2O4. In fact, that's going to be our second step. Step one, make sure your equation is balanced. Step two, write out your equilibrium constant, right? So we have that. Now, we need to plug in concentrations, and it tells us we have 3 moles in 0.5 liters. Therefore, we have 6 molar N2O4. Now, do we know how much N2O4 is going to react? Do we have any idea how much N2O4 reacts here? No. If we knew that, we'd be done. Because we can see that for each N2O4, we get 2 NO2. So we need to say, how much should we say reacts then? Let's say what? Let's say X reacts. So let's call the amount of N2O4 that gets used up X. If we use up X N2O4, how many X's of NO2 should you get? That's why the balance equation is so important. 1x here, 2x there. So we need 2x for NO2. So let's call the amount of N2O4 that gets used X because we don't know it. For each X of N2O4, we get 2x of NO2. And we can start plugging that into our equation. Our KQ was 6 times 10 to the negative 6. Our NO2 concentration was 2x. And remember, we squared it. And we started with 6 N2O4, but we subtract out the x because that's the one that got used up. Makes sense. We subtract out some. Now, look at this equilibrium constant for a second. We said that it's equal to the product ratio, reactant ratio. And here it equals 6 times 10 to the negative 6, or 0.6 1.0000006. And so we got the 6 from the question stem. It told us that we had 3 moles of N2O4 and 0.5 liters, so we got molarity, moles divided by liters. You always need your concentration in molarity to put that in. So that's where the 6 came from for the N2O4. That's how much we started with, and the X is how much we use. So how much product are we honestly going to be making here if our ratio of product to reactant is 0.000006? Are we going to have a ton of product and very little reactant, or very little product and a ton of reactant to get that number? You need a big product or a little product so that when you divide, you get 0.000006. Yeah, we need very little product and a ton of reactant. In fact, to get a number that small, our numerator has to be considerably smaller than reactant. So how big is X really going to be in this reaction? How big is X really going to be if almost no reactant actually reacts? It's going to be infinitesimal. It's going to be so small as to not be noticed. So you know what we do? X is so small, let's pretend it doesn't even exist. The number 6 minus X is going to be so close to 6 that there is no reason to leave that X there. Because if you leave that X there, you have to use quadratic formula. Do you need the quadratic formula on the MCAT? Is the MCAT testing your mathematical ability? Absolutely not. It's critical thinking. So this is going to make our life a lot shorter, make it a shortcut. If the MCAT was all about math, there'd be no way for you to finish it on time. No one would ever get in the med school. And so no. So a good rule of thumb is if your KQ is less than 1, you can usually say it. The MCAT's really good about making KQs really, really small or really, really high. If your KQ has a negative exponent, you can make the assumption that that X won't matter. If your KQ has a negative exponent, you can make this jump. Because in any case, if you've got a negative exponent in the KQ, there's so little product that you have a decimal number. That's a good way to remember whether to make X there or not. And so now we just have to solve. Multiply both sides by 6, we get 36. Divide both sides, or take the square root of both sides, and guess what? You end up with 6 times 10 to the negative third, and that equals our NO2 concentration. So this is the method that we're going to use. In a few pages, we're actually going to go through it step by step and see it. But it's good to put it into practice because it gives us some triage ideas. Does this question look like one for right now? Probably not. However, and this is a big however, this is not a question that the MCAT considers being the long, drawn-out math question that slows you down overall. This is one to come back when the easy ones are done. This is not the one to just say, I don't have to deal with this. Doing one equilibrium equation, one equilibrium constant, shouldn't be enough to keep you from touching it at all. Stoichiometry tends to be the ones that take a lot longer because they have so many more steps. So this is something you want to practice because this is something that we must be able to do a little bit faster. Luckily, our Kaplan method will make this faster. We'll codify that, though, in a few pages. We need to get back to the task at hand, then, which is Le Chatelier's principle. So if you increase the temperature, which way is this going to shift? Is it going to shift to the product side or reactant side? You increase the temperature. We look at the enthalpy. Note here the enthalpy is endothermic, which means that heat is a reactant. There we go. Heat's required, it's endothermic. Therefore, there's more heat. Therefore, goes to the product side. Goes over to the right. So the forward reaction will definitely be more favored. You get more NO2, and therefore it's going to be more red. So that's a nice, straightforward Le Chatelier principle question. Equilibrium constant solving takes a little bit longer. Le Chatelier principle, these should be some bread and butter, nice 3, 4, 5, 6, 7 second questions for us as well. And that's what we want to do. So it goes forward because we have an endothermic reaction. That's that. What about if you increase pressure? What do we pay attention to for pressure increases? What do we pay attention to for pressure increases? Yeah, gas. All that matters here is gas. So notice the left side. There's 1 mole of gas. Notice the right side. There's 2 moles of gas. Which way should you shift if the pressure goes up? And notice if pressure goes up, we know that means less gas, which means there it is. We got to shift over to the left. So it becomes more colorless. It becomes less red as there are fewer moles of gas on the left. Not too shabby. And that's our first system. Rock and roll. Win-win. Win-win. Now, number system 2. What would happen if you increase the amount of lead here? What would happen if you increase the amount of lead? Michael, nothing. Nothing. Why? Why will lead not affect equilibrium? And there it is, because it's a solid. You guys got it. It's a pure solid, so it doesn't matter. We only care about aqueous and gaseous phases. So you know what? If it's solid, don't worry about it. Since we don't put solids in our KEQ, they're not going to affect equilibrium. They don't affect the concentration overall. Oh, next. What happens to the pH? Or what would happen if pH increases? Now, this one is a very common way for the MCAT to coax us into comfortability. What does pH directly relate to? Because note, we don't have a Le Chatelier principle for pH and acidity and basis, but it means protons. So now pH increasing means it's more basic, which means there are fewer protons. And if we decrease the concentration of protons, now we can make a guess. Which way should this one shift if we make it more basic, if we lower the number of protons, if we remove the product? If we remove product, go to that side. So you know what? Increased pH means removing protons, which means we shift it over to the right. Forward is reversed. We're going to make more product because we got to make more protons. So don't just rush through them. Make sure to think your way through to get those points. Definitely something that we've got to have ready for us on testing. One more system. What happens if you increase pressure here? Will it shift left or right? Product or reactant? Forward or reverse? You increase pressure. Now think, if we increase pressure, which way does it shift? Will it shift to the side with more gas or less gas? There it is. Increase pressure, you shift to the side with less gas. Which side has less gas? Well, the left side has 1 mole. The right side has no moles. So guess what? It shifts forward. It shifts over to the right. So note, lack of gas is still lack of gas. 0 moles is still a number of moles of gas that we can do. So we want to remove the shift. We want to remove the pressure. So we shift it forward. There are going to be fewer moles of gas on that liquid side. That's exactly it. And so now if you increase pressure, then you can start seeing some of the gas shift back to liquid. That's kind of what a pressure cooker does, right? Take your water, put it in a pressure cooker, it boils at a much higher temperature. Why? The pressure keeps the liquid down. That's what atmospheric pressure is doing right now. The pressure on your liquid keeps it from boiling. When your vapor pressure equals boiling point, there you go. Right? And then, think about it. Take a soda can and squeeze it. Can you? If you take a closed soda can you compress it? If you take a can full of soda, no. Why? You can't compress a liquid. So you can't increase the pressure on a liquid. If you add pressure to a liquid, the liquid's going to keep dispersing. Gases you can. Like if I have a water balloon and I try to squish it, it pops. If I take a gas-filled balloon and squish it, it squishes. So you can't compress a liquid. That's why liquids won't matter in terms of pressure. Plus, since it's equilibrium, pure liquids don't matter anyway. H2O as a liquid wouldn't be part of our equilibrium equation. So since liquids don't matter, you don't have to worry about it. That's what we get there. Now, there's a lot more practice, and again, notice these are in the high yield chapter, especially Le Chatelier. Le Chatelier shows up in a lot of different formats, and can make a lot of your obtuse chemistry much easier. We've got to practice it and perfect it and get a good sense of where it shows up and where it doesn't. Now, how many of you have seen equilibrium constants called KQ, but you've also can remember things like KA and KB and KW and KSP, okay? What did we say earlier? What do those subscripts tell you? Yeah, they just specify a type of reaction. So when we start talking about KSP, do you think that we're going to completely change everything we've come to know about equilibria constants? Nope. All this means is you're looking at equilibria in a particular reaction, and it's dissolution. What does that mean? It means take your solid, throw it in water, watch it dissociate into ions. That's it. So when you see KSP, it's still an equilibrium constant. It's still products to reactants. The SP just tells you it's dissolution. We're going to watch as the ions dissociate from the ionic bond into the ions themselves. So the KQ for dissolution is called KSP. That's it. So the same rules are going to apply. So we set up our products over reactants. Our products here, we have AG. NCl, our reactants, we have AgCl as one. Not too shabby. Except there is an error with that equilibrium equation. What is the error with that equilibrium equation? What is there that should not be there? There's AgCl because it's solid. So when it comes to KSP, you're not going to have to worry about reactants ever. Why? The reactants are always a solid. When it comes to KSP, it's the same principle. It's just a specialized reaction. Take solid, watch it dissociate into aqueous ions. Always. So when you say KSP, you know what should happen. Ions form from the solid. The KSP, we're only going to worry about products. The reactants is solid. And note that ion product is where we are right now. KSP is where we're going. So ion product is nothing more than the reaction quotient for this specific type of reaction. How much product I have now versus how much product I have later. So we can compare ion products. If the ion product's too low, we've got to increase it. So how are you going to increase your ion product? Noting the ion product, again, is just like KSP. It just depends on the concentration of products, just the concentration of products right now. How can you increase your KSP? Or how can you increase, rather, your ion product? Now, Juliet, just make more product. To increase our ion product, we make more product. So which way should your reaction go? To the left or to the right? Yes, you go to the right. So to increase the ion product, we need to make more product. There are things that we can do to make more product, but the equation itself has to make more product to move forward. Note, you guys are starting to throw in Le Chatelier. Remember, adding concentration, adding reactants, that's if it's at equilibrium. If we're looking at IP less than KSP, it's not equilibrium. We're not going to be worrying about concentration change. At this point, we've got to get to the equilibrium beforehand. So we call this unsaturated. More of the solid that's already there can dissociate. If you put more in, keep dissociating. Now, if the ion product equals KSP, it's at equilibrium. We call this perfectly saturated. If you add too much, though, how can you lower your ion product? How can you lower your ion product? How do you lower it? Notice your ion product and what it depends on. The ion product depends on only one thing. So what is the one thing we can affect? And there it is. Yeah, you just got to lower your product. So how do you lower your product? Just go in reverse. What do we call it when once dissociated molecules start becoming solid and falling out of solution? What do we call that? And Annie, Kelsey, yeah, we have precipitation because Kelsey just said it. This is a supersaturated solution. It went too far. So the solid starts precipitating out. So if your ion product is bigger than KSP, you're going to precipitate. If your ion product is less than KSP, you're going to dissociate. And if your ion product equals KSP, it's a perfectly saturated solution. It's exactly where it wants to be. It's at the hotel, feet kicked up, drink in hand, watching TV, and relaxing. A good example of a supersaturated solution, if you guys are curious, Southern sweet tea. I don't know if you've ever had sweet tea in the South, but that stuff is sweet. Why? There's too much sugar in it for the liquid. So you heat it up, dissolve everything, cool it down, watch it precipitate. I grew up in the South. Anyone who doesn't like sweet tea is beyond me. But I can understand how it's very much an acquired taste, right? It's definitely something. It's definitely something that some people love, some people hate. It's just not. Now, if we're talking at KSP, we're talking molar solubility, which is the molar concentration of solute in a saturated solution. So if you start talking about molar solubility, then you know you have a perfectly saturated solution. You're at equilibrium. Now, solubility, and you guys read for solubility today, is usually in grams per milliliter of solute that can be dissolved. Molar solubility will be the same idea, but moles per liter. Now, before we get too far into it, how many of you remember all of your solubility rules that you read through? Yeah, kind of, not all. One thing I encourage you to look at, and my students, one thing I'm going to send you later today, is there is a song written by the chemistry department at Cornell that actually goes through the solubility rules, and that song is amazing. So, if you're having trouble with solubility rules, it's definitely something to YouTube. I am definitely no doubt going to sing this in any way, shape, or form. That would ruin the surprise, plus it's not my song to sing. But it's a good one. It's a good one. And so my students, I'm going to send you that link a little bit later so you can find on YouTube. If not, if you want to look at it, feel free to do so during the break or after class, but you'll get it from me a little bit later. Just to think about solubility. Now, common ion effect. Common ion effect is nothing more than a fancy term for Le Chatelier's principle. Nothing more than a fancy term. All it's saying is that, you know what? During your product, you're going to make some ion. If there's already product there, you're going to make less ion. Remember, product wants to shift it back, especially if we're talking about equilibrium. So if you take sodium chloride and you put it into, it'll dissolve more in filtered water than in a swimming pool. Why? Swimming pool has chlorine in it. So the swimming pool already has some chlorine in it, which shifts it back over to the left. So it's going to have more solid, therefore less dissolves in. One it goes. So, let me ask you this. We put AgCl in some water with chlorine. We decrease solubility. Let's say I put in AgCl into water full of iron. What is that going to do to the solubility of iron, of sodium chlorine? Of silver chlorine. Sorry, I keep saying sodium, but I know it's silver. Yeah, it does nothing. Why? Why will this have no effect on solubility? That's what it means to have a common ion. It's not enough just to have ions. They've got to be common, meaning the ion present needs to be an ion that's already made from the product. It has to be common to the reaction you're going to be carrying out. So since there's no chlorine and no silver, this will end up with no effect on solubility. So we're going to codify those rules we talked about earlier before we take our second break to learn how we can, in fact, solve any type of equilibrium question. And you can see there are two questions at the bottom of your book. Now, some of you may notice that the first one is slightly different. I'll tell you how to change it to match the one we're going through. But this is our method for molar solubility questions. Theoretically, anytime you need to solve for an equilibrium constant, this is the method to use. It's 3 steps. It works every single time. So step 1 is to write a balanced reaction. Step 2, find the expression. Step 3, plug it in. Those are your steps on page 197. So we're going to do this together on 2 questions. If the solubility of silver chloride in pure water is 1.25 times 10 to the negative fifth moles per liter, what's the value of KSP? And this is where the book error may be. You should have 10 to the negative fifth, not 10 to the positive fifth. That was a misprint in the most recent printing of the book. So if you see this question and there's no -5, make sure to put a negative. So the solubility of silver chloride of pure water is 1.5 times 10 to the negative fifth. What's the value of KSP? Step 1, write our balanced dissociation reaction. And since it's KSP, we know we're taking solid sodium or solid silver chlorine, and we're making silver and we're making chlorine. Step 2, find expression. And we know that it's nothing more than the products divided by reactants. But since it's dissociation, the reactants are solid, so we boot them out, forget all about it, KSP. Done. Now, we did this earlier. Do we know how much silver chloride is going to dissociate? Nope. So remember earlier, we said, let's say X dissociates. So if X moles of silver chlorine dissociate, what should that do? How much silver should we get? How much silver will we get here? Yeah, we should get X. For every 1 AgCl, you get 1 Ag. So X AgCl, X Ag. What about chlorine? For every silver chloride, there's 1 chloride ion in it. So for each X you dissociate, you should get X as well. So plug in your X for the concentrations. And that therefore becomes X squared. Ag is X, Cl is X, X squared. Now, question. What are you solving for in this MCAT question? Are you solving for KSP or are you solving for X? What is this question asking for? Notice, it wants KSP. So if you want a number for KSP, what number do you need to solve for? Yeah, I need X. So that's what this is. X represents molar solubility. So we plug in our solubility, solve for X, and we're done. So KSP is just going to equal 1.25 times 10 to the negative fifth to the second. Win-win. Do you really want to do 1.25 times 10 to the negative fifth squared? Probably not. We can make it much simpler by saying it's probably 1.3, but if we did it, we get 1.6 times 10 to the negative 10. Just square 1.25, get 1.6. Square 10 to the negative fifth, negative 5 times 2 gives you negative 10, and you're done. So question, how much sodium chlorine, or how much silver chloride are we actually dissociating here? Tons or little bits? How much is actually dissociated? Gurgit, small, Michael, small. Very little. In fact, on your MCAT, most of the time when you're dealing with equilibria, you're almost always going to be dealing with a reaction that doesn't go forward very far. Silver chloride, very insoluble. We can see it. Its KSP is so small that you know what, it's just not going to be anything helpful. There we go. We try one more. What's our first step? The molar solubility of zinc fluoride in water is 1.57 times 10 to the negative first molar. What's zinc fluoride's KSP? Step 1, write our reaction, balance it out. So we do that. And here we have solid zinc fluoride, and it's going to make zinc 2 plus and 2 fluorides. Note, that's why we wanted the molecular structure for it. Next, we write our KSP. And here, we're going to have the concentration of zinc times the concentration of fluorine squared. Remember, your balance coefficient becomes your exponent in the KSP. Now, what's our next step? After we've done that step, after we've set up our KSP or our equilibrium constant. Step 1, write out a balanced reaction. Step 2, set up KSP. Step 3, what? Now we just plug in. We don't know how much is going to be used, so again we say X used. And now note, if we use X moles of zinc fluoride, we get X moles of zinc. How much fluoride, though, do you get for each X of zinc fluoride that you dissociate? For each zinc fluoride you dissociate, you should get, and there it is, you get 2X. Because note, for every zinc fluoride, you get 2 fluorides. So if there's X zinc fluoride, you should get 2X. And so we plug that in. So note your expression includes the 2 and the square. You put them both in or you'll fall for a trap. So turn your balance coefficient into your exponent and then use your balance coefficient to remember just how many x's you're going to get there. So that's how we set it up. That's the chemistry behind it. If you don't do both, problematic, right? So while you square it, that's how you set up equilibrium constants. Balanced equations always become the exponent. Do them both. And so again, we're solving for KSP, so they have to give us x. And you'll notice that here we have 1.57 times 10 to the negative 1 to the third. Now, how can you make this easier on yourself? Because let's face it, 1.57 to the third is nasty math. Michael, you just took the question out of my mind. There is something you can do to make this easier. Something that makes it considerably easier. And we'll still get you the right answer. I don't want to do 1.5 times 10 to the negative 1 to the third. What number is close to 1.57? That's a lot easier to find it to the third. You can do 1.5. I go even 2. On the MCAT, 2 is going to be perfectly fine. 2 will be perfectly fine. So you could easily say, you know what, this is nothing more than 4 times 2 times 10 to the negative first cubed. And when you do that, you end up with 4 times 8 times 10 to the negative third, which gives you 32 times 10 to the negative third, which we can then go and substitute down to 3.2 times 10 to the negative second. So question, do you think that estimation will be close enough to get the right answer here? Oh yeah. One thing about your MCAT is most answers, you guys have seen this in homework. How many of you have noticed that many times the exponent is what's different in the answer choice versus the first number? Yeah. You know why? That's because they want you to estimate. Your answer choices aren't going to be things like 1.54 times 10 to the negative 2 and 3 points. No, it's not going to be that close. Also note, though, that you overestimated, so the number you get is going to be slightly larger. So you need a number that's less than 3.2, but not very far off from it. And that's exactly how you can go back and estimate. That's how you make the question easy. Do your molar solubility. These questions can be done in a good 45 seconds flat. We just have to practice them. One way to make it easier is to recognize the possible products that you could get. Notice the first one we had x squared when it was a 1-to-1 relationship. Here we had 4x cubed, right? Where we had 1 and 2. You might also end up with one where you have, say, 1 product of 1 and 3 products of the other. Like if you did FeOH3, you get 1 Fe and you get 3 OHs. So in a case like that, you'd end up with 27x to the 4th. So one way to make it easier in setup is to recognize just how many ions you're going to form from that dissociation. And when you figured out how many ions you're going to form from that dissociation, remember it's either going to be x squared, 4x cubed, or 27x to the 4th. Did I make 1 of each ion? Did I make 1 of 1, 2 of the other? Did I make 1 of 1, 3 of the other? And now we've seen an example of each of those 3. Those are without a doubt the most common. And in our third passage, it's going to be something that's going to save us a lot of time, a lot of energy, a lot of effort, and get us a lot of points without a lot of work, which is nice. All right, friends, you know what time it is. We're really 2 hours in the class. So it's been an hour since our last break, so go grab a snack, use the restroom. See you guys back in here in 5 minutes to go over our last content of the day. The temperature. And so if you're trying to figure out the relationship between heat and temperature, this is a good equation to do that. The heat added equals m times c times delta T, where m is going to be your mass in grams, c is going to be your specific heat in calories per grams Kelvin, or even maybe in grams per degree Celsius, and T is your temperature change. Now, C is just the amount of heat required to raise the temperature of a mass unit, 1 degree Celsius or 1 degree Kelvin. The only one you have to know is water. So what is the specific heat of water? What is our specific heat of water? If we're looking in joules, it's going to be 4.184 joules per gram Kelvin. If we're looking at calories, and typically the MCAT focuses more on calories, it's going to be 1 calorie. But it's not bad to know them both. You will need to know your specific heat of water without a doubt. Now, this equation looks a little bit familiar. What does it kind of look like? MC delta T. It looks like MCAT. So just imagine yourself having heat put on you and you trying to keep your cool and your calm on test day. It just looks like the MCAT. The MCAT adds heat, but you know what? We're not going to let it get to us. So our test, believe it or not, going to help us get some points. Now, it's one thing if they want us to get the heat we've added. It's another thing if they want heat capacity. And so heat capacity is just M times C, or the mass times the specific heat. So recognize if the question's wanting the heat added or the heat capacity. Heat capacity doesn't show up as often, but you know what? If it does show up, we want to know how to define it. Nice, straightforward think step, nice, straightforward question. Now, does every last calorie of heat you add to a system always go to heat it up? When I add heat to a system, will it always increase the temperature? No. Sometimes it will, sometimes it won't. Name for me an example where you can add heat to a system, but temperature will not change. To prove to us that heat and temperature are not necessarily the exact same thing. And John, Chelsea, Stephen, Ruth, Dakota, Zulia. When you're melting, when you're boiling, when you're changing the phase. So at a phase change, heat is doing work. And we can think back to our equation, right? Where you have U plus or minus W equals the amount of internal energy. So if heat goes to just directly to internal energy, temperature goes up. If heat does work, temperature doesn't go up. And phase changes are a great example of where heat does work. It's got to break the interactions, holding them together. It's got to hold everything together. And so now if we look at an actual heating curve, we've got to recognize when we can use Q equals MC delta T during the heating up. So when you're within a phase, MCAT, when you're trying to change the phase, note that you're just going to take the mass of your object, be it small or large, and the transformative heat, or the heat it requires to change that phase, to break those interactions. Like here, where you might have the heat of fusion because you're converting water to ice or fusing it, or heat of vaporization when you are turning water into steam or vaporizing or boiling it. So note that while you are breaking those intermolecular interactions, while you're changing the phase, you're adding energy, but temperature remains the same. So at boiling point, at melting point, you see both phases, and your temperature won't change until every last phase bit has changed over. So we do need to recognize exactly what those different phases are going to be. All right. And so, Michael, yeah, size isn't really going to matter if we're looking at breaking the bonds. If you want to heat up a big body of water, it's still going to have the same specific heat because it's still water. So you're just going to have to require more heat to make that happen. But you can heat it up, and then you can watch it boil off. So it doesn't really matter about the size, at least in terms of the MCAT, when it comes to Q equals MC delta T. Now, number 11. Notice the answer choices are all in the graph. So guess what? The graph is going to be important. But I want you to read this question, and I want you to think and tell me, which choices do you feel comfortable eliminating just on point, having read through this question stem itself? Which ones do you feel comfortable just saying, no, I don't think it's going to be it? A good strategic guess, a good strategic move, a good medical move, if you will. Eliminating things we know it can never be. And you guys are, yeah, get rid of ethanol, get rid of water. Why? We want the lowest boiling point. So if you want the extreme answer, you probably need the extreme choice. Ethanol's in the middle, water's in the middle. So it's either going to be diethyl ether or iodine. Now, we need boiling point that relates to temperature. And I want you to think back to Bio 1. If one axis is going to give you the answer, how can you move forward? What's our way of proceeding with a graph? If one axis is going to give us the answer, in this case, boiling point, because we want temperature, what do? Next step, we think this axis gives me the answer, therefore the other axis gives me the clue. Keisha Safari, exactly right. So note, the other axis has to be related. So there's got to be a way to relate vapor pressure, and boiling point. So what is vapor pressure? Let's start there. What is vapor pressure? Sometimes it's good just to start by defining. It gives us a place to start, and it gives the way to think it through. As long as we know what we're solving for here, lowest boiling point, now we can start dissecting. What is vapor pressure itself? And I like where Michael's going. Vapor pressure, like, let's say that you grabbed a soda and you smell the soda, or you put your nose to it. Can you smell the soda when you put your nose to the can? Yeah. Why? There's vapor pressure. It's the pressure above the liquid. Like if you look at any liquid, some of the liquid molecules have escaped, and they're just kind of sitting above the liquid. That's the vapor pressure. So vapor pressure is literally just the pressure above a liquid due to the molecule escape. Now, the question also gives us one more point of information. It gives us atmospheric pressure. It says it's 0.5 atmospheres. So we got to think, is there a way to collect vapor pressure above a liquid, atmospheric pressure, and boiling point? Is there a way to connect those three pieces? Because those are all the clues they've given us. We know vapor pressure's got to help us. We need boiling point, and we've got atmospheric pressure. There's got to be a way to connect it. And this goes back to one of our definitions. Boiling point. It occurs when vapor pressure equals atmospheric ambient pressure. So right now, gas is weighing down on liquid. It's keeping the liquid from escaping. So Jessica just said it. Christine just said it. When vapor pressure equals atmospheric pressure, that's when you get boiling. So we know the atmospheric pressure or ambient outside pressure is 0.5 atmospheres. Which vapor pressure should we go pay attention to then to find the boiling point here? Yep, we need 0.5 atmospheres. So you know what? We look at the graph. Which of these hits 0.5 atmospheres at a lower temperature? Is it diethyl ether or is it iodine? Just draw a middle line. Which one hits vapor pressure at 0.5 at a lower temperature? Diethyl ether, diethyl ether, A. So when given a graph, one axis gives you an answer, go immediately to the other axis and think, how can I connect these? But this definition of boiling point isn't the traditional one people think of. This is the one the MCAT loves to test. When vapor pressure equals ambient pressure, that's when you see boiling. That's when you hit that temperature that allows the vapors to escape. So know that equation, know that definition. And so note, phase changes can be helpful. There's some practice on phase changes in that thermodynamic and thermochemistry test. Particularly the first passage is a good one to give you some practice. We look at a phase diagram as well. We have to recognize what the different phase changes are called. We go from solid to a liquid, that's going to be the melting point. We go from liquid to solid, that's freezing. We go from liquid to gas, that's boiling or vaporization. We go from gas to liquid, that's condensation. We go from solid to gas, that's sublimation. And if we go to gas to solid, that's deposition. So no, you may be given something called the heat of sublimation, which just means you're converting a solid to a gas. Or you might be given the heat of vaporization, which means you're just boiling a liquid to a gas. Or you might be given the heat of fusion. You're just melting. So note, if you see those subscripts, you have to recognize what's happening, which phase change is occurring, because the MCAT's going to give you points for knowing. Is it possible to have two phases at once? Is it possible to get a solid and liquid at one time, or a liquid and gas at one time, or a solid and gas at one time? Yeah, you can. And don't, when it comes to fusion, fusion is what they call melting. It may not seem like the most, it's one of those few times you're like, chemistry may not seem like the most logical nomenclature. Yeah, it's kind of an oddity, but it's good to know the oddity, right? Yeah, you can have it. Notice that's what these lines indicate. These lines indicate where you can see a solid and a liquid, where adding temperature is just going to break intermolecular interactions, right? And note, you can see all three as well at the triple point. So there's a point where you can see gases and liquids and solids at a specific pressure and temperature. So all three phases can exist at once. There's also what we consider the critical point, above which we can no longer tell whether it's a gas or a liquid. What do we call that phase up here, above that critical temperature and above that critical point? And Michael, you beat me to the punch. It's called supercritical fluid. Now, a lot of people will tell you supercritical fluid is the same thing as plasma. It's not. Plasma is a little bit different than supercritical fluid. You do need to know what supercritical fluid is. So you do need to be aware of it, what it is. It's at such a high temperature and pressure, it has properties of liquid and gas, and you can't determine which one it is. So you've got to go beyond what we consider the critical pressure and the critical temperature to get there. Now, water's phase diagram does not look the same way as this one. How is the phase diagram of water different than this traditional phase diagram? How is the phase diagram of water different than the traditional phase diagram? Kimberly, Michael, proceed. Has everything to do with that solid liquid line. Instead of it being positive like it is here, it's negative. Now, is that really important to us? That if you look at the phase diagram of water, that ice has that negative slope? Kinda. Because of things like that, ice floats. Is it really a big deal that ice floats on water? Yeah. If water froze from the bottom up, we would not be here. We would not have ever crawled out of the evolutionary ooze of the ocean because things would have died off after each freeze. So it's kind of a big deal. One of the reasons ice floats on water is it's less dense. So as you get it colder, the pressure actually goes down a little bit, and that's going to affect the density. So ice goes to the top, water goes at the bottom, and that's going to help us. So as water freezes, it expands, therefore it's less dense, therefore it floats, therefore it's a good thing for us. And we'll talk more about that as we get into liquids and solids in physics 3. Now, is water the only molecule on Earth with a negative slope between the ice and water interface? No. It's just the only one we have to know of. Like bismuth. Bismuth, which makes up Pepto-Bismol and keeps your stomach from destroying itself, right? Bismuth also has this, but the MCAT doesn't care that you know about bismuth. The MCAT cares that we know about water. Water's kind of a big deal. There's no surprise. Now that then takes us to our final topic of chemistry 2, which are colligative properties. Now, colligative properties, these are going to be properties that are based on number of particles, not the chemical nature of particles. So more particles, more effect. That's what a colligative property is. Sheer number. It's all about sheer number. And we've already talked a little bit about one of them. We talked about it in Bio 1. Name for me something that cares not about the chemicals, but about the number of them. Name for me something from Bio 1 that depends on the chemical number, not the chemical nature. Osmolarity. Cyrus, there it is. Osmosis. The fact that water goes from hypotonicity to hypertonicity. Osmosis is a good example. It doesn't care about what the chemicals are. It just cares about the number. That's a great one. So you see osmolarity, things like osmotic pressure, which we'll talk a little bit about in biology, a little bit you'll read about before then. And what we're going to talk about tonight, boiling point and freezing point. Because boiling point and freezing point both depend on molality, not to be confused with molarity. Molality is moles of solute divided by kilograms of solvent. So if you add more moles of solute, what should you do to your molality? If I add more moles of solute, what will that do to my molality? Yeah. More solute, higher molality. And no, we usually use the lowercase m. So lowercase m, molality. Uppercase M, molarity. And so now if you have 1 mole of sodium chloride and 1 kilogram of water, you have a 1 mole solution. There was 1 mole of NaCl, there's 1 kilogram of water, 1 mole. So that's how we get little m molality. Now the first colligative property we're going to talk about is vapor pressure. Right? And note we have an equation for this, where PA is going to be the actual vapor pressure above the solution, XA is going to be the mole fraction, and PA naught is going to be the normal pressure without solvent. So what you think? You're boiling water and you throw some food in. What happens to your rolling boil as you throw food into the water? Yeah. If I'm boiling water and I threw food in it, it slows down. So you take your water, throw your pasta in, watch the water stop boiling until you keep heating. That's because solutes lower vapor pressure. And we can even kind of imagine how this fits together. So your mole fraction means moles of what you're interested in divided by total moles. So I want us to look at 2 solutions to give us a better example. Let's say that in one solution, we have 10 moles of A, and let's say 2 moles of B. Then let's add some B to it. So that now we have maybe 10 moles of A, and let's say 5 moles of B. Now the mole fraction here would be 10 over 12, because you have 10 moles of A and 12 total moles. Over here, it becomes 10 fifteenths. Now 10 halves, or 10 twelfths, that's 5/6. 10 fifteenths, that's what? 2/3. So what is happening to mole fraction as you add more solute? As you add more solute to your solvent, what happens to the mole fraction of solvent? Like here, the mole fraction of solvent A. As I add more solute, I went from 5/6 to 2/3. If I keep adding, I'll go to 1/4, and then I'll go to 1/2, then 1/4, then 1/6, then 1/8. As you add more solute, your mole fraction of solvent goes down. So as you add more solute, you add more total moles, but there's the same amount of solvent you started with. So as you add more solute, your mole fraction of solvent goes down. Well, if I decrease my mole fraction of solvent, what's going to happen to the vapor pressure? If I decrease XA, I'm going to decrease it as well. It's a direct relationship. Notice multiply, it's just right there. Nice direct relationship. Increase one, increase the other. Decrease one, decrease the other. So as you add solute, you lower the mole fraction. And if you lower the mole fraction, you lower the vapor pressure. So I want my water to boil, yet I've lowered the vapor pressure. How am I going to get it to boil then? I want my water to boil, but I've lowered the vapor pressure. How can I get it to boil again? What do I have to do? Well, think about it. You have your boiling water. You throw your pasta in, it stops boiling. How do you get your water to boil again when you're cooking? When you threw the solute into your solvent. How did you get it to boil again? Remember, adding solute lowers vapor pressure. If you have a pot of water on and you throw pasta in it, how do you make it boil again? Well, you leave it on the stove and you leave the temperature on. You just give it more heat. How do you get vapor pressure? We get the solid, we get the liquid to boil off. So note, and this is something that gets a lot of people in trouble and costs a lot of points on testing. We are lowering vapor pressure. So we have lowered the vapor pressure. To boil, vapor pressure has to equal atmospheric pressure. How do you get more vapor pressure? You increase the heat. You add more to it. So if you lower the vapor pressure by adding solute, what is that going to do to boiling point? Yeah, you increase it. How many of you have ever heard that if you put salt in your water, your food will cook faster? How many of you have ever heard if you put salt in your water, your food will cook faster? Why? It's right here. It's not because the salt does anything special. If you add solute to your liquid, you lower the vapor pressure, which means then to make it boil, you have to add temperature to it. So adding it increases the boiling point, which means it cooks at a higher temperature, which means it would get cooked faster. That's why it would work that way. Now you have to add a lot of salt. Why? Because the change in boiling point depends on molality, which means you have to go add moles of salt before you even see any kind of change there. So if you add solute, you increase the molality. Right? You increase the molality. You increase the boiling point. So lower vapor pressure, have to add more temperature to increase the boiling point. And the change in your boiling point is going to depend on things like Van Hoff factor, which is I, Kb, which is your atmospheric boiling constant, and little m, molality. So let's think about it. You add more solute. So if I add solute, what is that going to affect in this equation? If I add, let's say, moles of solute to it. If I add moles of solute, what will that affect in this equation? Well, we increase moles of solute. Aza, Gerja, yeah. Add moles of solute, you're going to increase molality. Remember, molality is moles of solute divided by kilograms of solvent. Right? So we increase molality. What's that going to do to the change in your boiling point? If you increase molality, if you add solute to it, it should increase the change even more. Increase M, increase the change. We have to remember that we increase the boiling point. There you go. Nicely done. Now, Van Hoff factor can be a part that drives people crazy because it seems like something you haven't really talked about before. It's actually one of the more simple things that we can encounter in terms of Gen Chem. And so when it comes to Van Hoff factor, when it comes to Gen Chem, Van Hoff factor literally is going to be equal to the number of moles of solute particles you get from 1 mole of starting material. So let's say we look at glucose. If I put in 1 mole of glucose, how many dissociated particles am I going to get? Yeah, if I throw in glucose, I get 1. Glucose doesn't break apart. So 1 mole of glucose gives me 1 mole dissociated particles. What about 1 mole sodium chloride? Yeah, we need 2 moles of dissociated particles. What about a mole of sulfuric acid? Ding, ding, ding. We get 3 moles. So note the Van Hoff factor of glucose would be 1. You got 1 mole of dissolved particles from 1 mole of start product or start reactant. The I value for sodium chloride would be 2. You get 2 moles per mole of sodium chloride. Sulfuric acid, that'd be 3. You get 3 moles of product from 1 starting mole of H2SO4. So if I gave you an equal amount of glucose, sodium chloride, and sulfuric acid, which one will affect boiling point more? And there it is. Increase your I value. Increase your change in boiling point. And you guys got it. Now, why don't we add sulfuric acid to our water? Well, that would hurt us. And you guys are right. The reason that the salt thing tends to be a myth is we just don't add a lot. You know how many grams of salt you have to add to get a mole of salt? All you're going to taste is salt. It's going to be so salty that. So salt is for taste more than anything else, but you can see that as you add more and more, you'll increase the boiling point more and more. And then KB is just a boiling constant. If we need that constant, guess who gives it to us? That's the MCAT's job. So if you add salt, you lower vapor pressure, which means you have to crank up the heat and make it boil at a hotter temperature. So adding solute increases the boiling point by decreasing the vapor pressure. Win-win. What about freezing point, though? What if you take your solute and throw it into your solution? Yeah, it's going to lower the freezing point. And so now you can find the change in freezing point and how it depresses, again, by Van Hoff factor, our freezing constant, and molality in moles per kilogram. So again, if you were running the city and you were in charge, if you were running the city and you were in charge of making sure that things didn't freeze, which would be better to put on the road? Sugar, salt, or sulfuric acid? Which one theoretically would be better? Sugar, salt, sulfuric acid. Yeah, sulfuric acid. Why? Why would an equal amount of sulfuric acid be a better choice for lowering the freezing point so that water didn't form ice? There's more it's Van Hoff factor. More bang for your buck. Now, why would you not do it? And Michael, you just took my joke. You don't put sulfuric acid on there because it'll eat the road away. And that's definitely not something that we want to incorporate. No apologies. Good jokes should be shared like that. It could hurt. So there's what it is. And that's why we drink tea. So that's it done, my friends. So you've made it to the end of Gen Chem 2, and that brings us to our final passage of the day. Now, I want you to look through this passage really quickly and preview it and tell me, there's something about this passage, or at least this end bit of homework, that's going to be something we haven't seen before. As you do a quick flip through, there are discretes. So I'm going to give you 8 minutes to work on questions 12 through 19. Actually, I'm going to give you 8.5, I'm going to give you 9 minutes to work on questions 12 through 18. Well, that being said, where should you start? Should you immediately just jump in and start reading and hammering, or should you jump over to the discretes? Go for the discretes. Get them done first, get them done comfortably, then go back to your passage. I want you to use these next 9 minutes the exact same way you're going to use them on test day, and when you're done, we'll come back, discuss the answers, and we'll call it quits here right around probably not too much longer. But go do practice. I'll see you guys back in here in 9 minutes after you have a chance to work on questions 12 through 15 on the passage, as well as 16, 17, 18 as discretes. Get your answers in the poll, and we'll see how we do. Good luck, everyone. Okay, team. Let's just see how we did on this final passage. Now, 9 minutes. So let's start thinking about time as well. 9 minutes. Was that too much time? Not enough time? And then these are polls that show for you. There may have been a moment of the room acting up a little bit for us. So hopefully as we go through, you'll be able to see the polls and put your answers as we go through. We'll move the poll over here to the left-hand side, the right-hand side rather. You guys still can't see anything in the poll? Let me hide and bring it back. That way you guys can vote. So I was watching as you guys were going. No one was voting. Maybe one or two people were voting at a time. Just like, oh, maybe that'll help out as well. Now more, and that's kind of what I was going about in terms of the time, right? You guys still get okay. You know, we don't worry about the polls right now. The room's trying to give us the room maybe gives us a problem. That's okay. Part of getting ready to be a doctor is rolling with the punches. If we let something freak us out, then you know what? No reason to leave to come back in just a We'll just go through the answers. You guys can check on your own to see if they worked out for you or not. So, as we go through, now note, 9 minutes may seem like not much time. However, I want you to think back to it again. Do you think on test day that there were some questions here that might have been those that you would guess on and move on so that you would have those minutes to go elsewhere? Absolutely. So 9 minutes may not feel like a lot of time because the questions here weren't designed to be done in 9 minutes. The questions here may end up actually taking 20, 25 minutes. Is that acceptable, though, for 7 questions to take 20, 25 minutes on testing? Not at all. So if we let those questions slow us down, we're now seeing the problem that can come from that. We've got to be really careful with that. If we let one passage take 20, 25 minutes, that time's got to come from somewhere else, and we've got to learn what those harder, longer questions look like. Now, in road mapping, there are a lot of good clues in this rather short passage that we want to catch in here. Now, for instance, there's a good extreme keyword in this passage that I hope that I wanted you all to catch. In this first paragraph, what was the extreme word that you might have caught to help understand a little bit more about this Volhard? We see exact to get an exact reading, but also, Chelsea, the word must, right? So we're talking about experiments. The method for a silver determination, we have this new method, and we use this indicator. The solution must be kept fairly acidic to prevent iron oxide trioxide formation, and then just shows us how it works. It gives us a more accurate reading. We have the relevant solubility. And so we get the Volhard titration. We're going to determine halide ions and silver ions. From that, and we get some KSPs. And then we get the actual experiment, and it turns out sodium thiocyanate was contaminated with sodium hydroxide, and our indicator never formed. So that might be a clue to deal with. Now, question 12. Is this the now or the later question? Question 12. Is this the now or the later question? This is the later question, without a doubt. Because note, it's asking us, now first off, the question answers look like something we would handle now. Because they're just clues, yes, no. But what kind of info are we going to need to determine if there's precipitate forming? Oh yeah, we're going to need to do some math. Specifically, we're going to have to look at the amount in solution. We're going to have to compare it to the KSP, and we're going to have to determine is ion product greater than KSP, because that's when things precipitate. So we've got to know how much ion product there is. Is that comparable to the KSP? And if so, just how comparable is it? So this one definitely takes us a little bit longer because we're going to have to look at the amount of thiocyanate, and we've got to look up the amount of Ag. Now it tells us that we have 1 mil of a 1.0 times 10 to the negative fifth molar solution. So we have 1.5 times 10 to the negative fifth moles per liter, and it turns out we only have, 1/1000th of a liter of it. Because we're looking at one. mil. But when we take our 1 mil and add the 3 mils, we end up with 4 mils overall. So we've got to take it. Remember that in 1 liter, we're going to have 1,000 milliliters. And we actually have 4 milliliters as well to make this overall conversion. So when we do all this math, turns out that we have right at 0.25 times 10 to the negative fifth molar SC negative. Okay? Then when we look at silver, notice here we have, again, 1.0 times 10 to the negative fifth moles per liter. And again, we've got to convert over to mils. And we got, in 1 liter there, 1,000 mils. And here again, we got to remember that we have just the 3 mils of it in the total 4 mils overall. Sorry, I skipped a step. Notice how many steps there are. Does this look like something you want to attempt when you're really in the mode of it? When you're really under the gut? No. Because now we have 3 mils of this stuff, but we're going to end up with 4 mils of solution. So we have all these little bits and pieces that we have to go through. In the end, we eventually get here 0.75 times 10 to the negative fifth molar Ag. And then to find the ion product, we take those concentrations and we multiply them together. So we multiply those together, we're going to end up with 0.75 times 10 to the negative fifth times 0.25 times 10 to the negative fifth. Do all your math, you end up with roughly 1.9 times 10 to the negative 11. So your ion product of this is 1.9 times 10 to the negative 11. What is the KSP for this solution? And Taurus, where did the 1/4 come from? You're adding 3 mils of it, so you need the exact number of moles. But remember, you've got to get concentration, so you have 4 moles. So you have 4 milliliters total. So you've got to incorporate how many mils of silver you get, then incorporate how many mils of total solution. What's the KSP of this? And notice the passage tells us, we look at it, Adam just got it. The KSP is going to be equal to, in table 1 times 10 to the negative 12. So should there be precipitate here? If IP, in fact, is IP greater than KSP? It is. So if IP is greater than KSP, we call that supersaturated. If it's supersaturated, will there be precipitate? If it's supersaturated, it'll be precipitate. Supersaturated means there's too much and it precipitates out. So guess what? It can't be A, it can't be B. Will there be precipitate? Yes. Now we can go to the reasons. Which reason do we choose here to make sense of this one? C or D? And at that point, it's got to be answer choice D. Yes, because the concentration is in fact above saturation levels. C doesn't make a whole lot of sense. In fact, we could prove C is wrong. How can you prove C is wrong? Because we could go about this in a completely different fashion. That these are completely insoluble. And there it is. Nitrates. Sodium nitrates are soluble. So, boot it out. So you can totally get rid of this. And more, this is the typical long problem. This particular passage set had a few long problems in it to get you used to looking and saying, this was going to take me forever. This one does take a while. There's not a lot of shortcuts, but there is some reasoning we can do to make it easier. So here, you're going to say, you know what, C makes no sense. There's got to be some solubility based on my rules. So therefore, let me at least guess A, B, or D. But this is going to be one of your typical long-term problems. Now, 13, though, is not. 13 is one that we should have jumped to, because notice the answer choices are logic. Notice we don't need math. Notice we can solve this one a little bit easier. Why is it that this precipitates before iron forms? Well, let's think. What has to be true if something's going to precipitate first? You think of it again. What does it mean to precipitate? When is something going to precipitate? Yeah, when your ion product is way too big. Too much in solution, start precipitating out. It's based on KSP, right? So if this one precipitates before the other one ever even forms, what does that tell you about the equilibrium? There it is. Dalton, yeah. It's got to reach it first. So note here, if it's going to be true that we're talking about a precipitate forming first, the precipitate must hit equilibrium first. So one's going to precipitate way before the other, meaning one is less soluble, meaning one has a lower KSP. Which of those answer choices then matches this idea of the lower KSP? You guys did it. Beautiful. So no, number 12 may have shaken us a little bit, but number 13, win-win. Right? Number 12 may give us some trouble, but number 13, a lot easier to deal with. Now, number 14, does this look like a now or a later question? Which one has the highest molar solubility? Now, this one seems maybe a little bit later, but it's actually not as bad if we approach it systematically. How are we going to find molar solubility if all we're given is KSPs? Well, we just use our three-step method. And I like where it's going. Let's eliminate it. Remember, KSP just equals our concentration of product. And remember our shortcut from earlier. We're either going to end up with a KSP that equals x squared if there are just two products, where it's going to equal 4x cubed if there are three products, and equal 27x to the fourth if there are four products. So we just need to set it up and plug in x. Now, should we test each and every one of these? Should we honestly go and test each and every one of these? No, not at all. How many products are you going to get from A? Like if you take BaCrO4 and split it up, how many products do you get? You get 2. What about AgCl? If you split AgCl, how many products do you get? 2. What about aluminum trioxide? How many products do you get now? Here we get 4. What about PbCO3? How many do you get here? 2. So we want the highest molar solubility. Now, if we look at the 3 that give us 2, we only need to test one of them. Which of those 3 should we test? If we want the highest molar solubility, remember that more KSP means more soluble. Higher KSP means higher solubility. So which of those should give you the highest solubility of the 3, considering that their KSP is always going to be equal to x squared? So if you plug in that x for x squared, you're going to get, and there, test A. B's lower than A, D's lower than A. A is your best chance in case of this. So we try A. So if we look at BaCrO4, our KSP is just going to equal x squared. Plug in your x. Or rather solve for x, so we end up with 2.1 times 10 to the negative 10th equals x squared. Take the square root of both sides, you get roughly somewhere around what? 1.4 times 10 to the negative 5th equals x. So the molar solubility here is going to be 1.4 times 10 to the negative 5th. Then you just, so note, lower KSP for AgCl means it's going to have a lower solubility than A. D has a lower KSP, therefore it has a lower solubility. All we need to do then is test out C. And since there are 4 products, we know that for this one, for AlOH3, our KSP here is just going to equal 27x to the 4th. And all of that has to equal 3.7 times 10 to the negative 15. And we start doing our math at this point. Equals 27x to the 4th. If you do your math here, you end up with x is roughly somewhere around what? 1.3 times 10 to the negative 4. So which of those two has a better Molar solubility. In this case, it's going to be C. So now here's a good chance for extremity. But we didn't have to test everything. And we know that solubility equations like this are the ones we want to go to in kind of that second pass in the passage. Number 13, definitely quicker. Number 14, let's hit it before we leave. Number 12, let's guess and only come back if nothing else is going to be there. So this is a good one, John, to maybe get the other ones in the passage and go back and try. Number 12 is the example of the one that completely skipped over. Now, do you need to do math? You do want to do the math here. I've seen this question on the MCAT where people will assume that since AlOH3 has more ions being made, it's got to be more soluble. And they give you a number that actually causes it to be less soluble. So you do need to do the math on these questions just because you're comparing very close pieces. Right? Because the one that makes the most product, I can name two questions from through two of the MCATs I've taken where the bigger product was the one that made the most product, in fact, was not the one that did it. It's a good guess, but it doesn't necessarily have to be true. So this is one that we can guess on and feel comfortable with, but if we have time, we should go back and check. And just look at how does PbCO have 4? It doesn't. It just has 2. That 4 represents aluminum trioxide. PbCO3 gets lead, and then you get the CO3. So go to 15. Now, is the passage needed to solve number 15? Why is there no endpoint? There is paragraph 1. What did paragraph 1 say? What was that key word in paragraph 1 that if we overlooked it, we're going to lose some points on this one? Must. It must be acidic. So what happened in the student's test? Well, we go back and look at the student's test, experiment number 1. The experiment requires acid, but the student put in NaOH. The base ruined it. The base ruined it. So which of these answer choices gets to what the passage was hitting at? It must be kept acidic to prevent FeOH3 formation. Remember, the passage says it must be acidic to prevent FeOH3 formation. And John, there it is. It's got to be C. It's got to be C. FeOH3 is completely insoluble. And we get that from the table. You look at the table, the KSP for FeOH3 is off the charts nothing. C is the one we want. So no, there are no cations we're worried about necessarily neutralizing in it. Because remember, you're talking about neutralizing, you're talking about acid and base, not base and cation. You need protons, you need hydroxides. Right? And A is wrong because we have no information along those lines. It told us that it's got to be acidic to prevent FeOH3. A may be true, but since it told us what must be true, A is an overreach for us. It's not necessarily that A is wrong in general, in chemistry terms, but it's absolutely wrong for this MCAT. The MCAT told us FeOH3 will form, therefore FeOH3 is bad. So if we go out from what the passage says, we're going to throw in a lot of extra info and we lose it. So A is just out of scope. That's the answer we fall into when we don't read the passage or research it. And it's a good sign to keep in mind. But you guys started with these, and this is good. Discretes tend to be a lot faster, a lot easier, a lot better. Win-win. Number 16, we have ourselves a nice little decomposition and redox reaction. We can see one product into many, and we can see the electrons moving. It's not combustion, there's no CO2. It's not neutralization, there's no acid and base. It's not Lewis acid and base. We're not taking two molecules and fusing them together by sharing their electrons. All we're doing, take one, make multiple. So number 16 is D. Number 17 is one that we would need to use our methodology to solve out here, so we would need to plug in. The only thing we have to keep in mind, though, is sodium fluoride. Why is that going to be important to keep in mind? And there it is. It's a common ion. Now, do common ions make our KSP math easier or harder? Turns out, it seems like it would make it harder. It makes it a lot easier. We set up our KSP. Notice here, our KSP is just going to equal, and we're looking at calcium fluoride, so we get calcium, and we get fluoride, right? And when we do that, we know that the KSP is going to be 4.9 times 10 to the negative 11. Well, when we take our calcium and build our equation, right, calcium fluoride, we're going to end up with calcium aqueous and 2 fluorine. So we know to square it. When we plug in our x's, we know we're going to get x for calcium and we're going to get 2x for fluorine. So we end up with 4.9. No, here's the thing though. Some of the fluorine comes from sodium fluorine. So our concentration of fluorine is actually going to be 2x plus 0.7. Now note the KSP here. It's incredibly small. So we're going to make little fluorine. We're going to make very little fluorine. So how can we make our math easier when it turns out we're not going to be making a whole lot of product? There is ignore the x. So you know what we end up with to make this easier? We call this x times 0.7 because 2x is going to be considerably smaller than 0.7. So really, all we have is 0.7x. Do the math, end up with answer choice B. You end up with x equals, or squared, so rather you get 0.49x. Sorry, guys. This is why you don't rush through math, right? You get 0.49x squared, take square root, divide, you get 1.0 times 10 to the negative 10. And again, note the exponent was really all we cared about. So we didn't have to worry a lot about the front number. We just need to know the exponent as well. Right? Now, why can't you ignore the first x? You can't ignore the first x because you're going to get some calcium in there. Fluorine you can ignore because the fluorine you add is so minuscule that you won't be able to tell that the fluorine came. But calcium wasn't there before. So you can't say there's no calcium, there's going to be some. We're just saying the amount of fluorine is so small that it's going to be unnoticeable versus this 0.7 that we already have. And then we go to the last one, and you guys tell me. And Chelsea, no. You tell me, what would happen if we decrease the volume? Well, we think decrease the volume means increase the pressure. We increase the pressure, go to the side with less gas. You guys are saying A? There it is. So nicely done. Oh, well. Now, the beauty of this passage is twofold. One, we got to practice our strategy and see when questions take longer and take shorter. Two, we're getting a better sense of topics that might take longer. So if you see a passage about solubility and KSP and saturation points, is this a passage you think for now or later? Oh, without a doubt. It's one for later. Because on test day, this passage is designed to be a killer. Why? If the MCAT's easy, then no one gets into med school because everyone gets everything right. But these are the types of passages that we as Kaplan students are going to have a tremendous advantage on because we recognize how much longer they take and we go proportionally. Can you imagine the student who hits this passage first and starts there on test day? Who would you rather be? The student who starts on that passage because it's passage number one, or the student who realizes, oh, thermochemistry, solubility, I'm going to come back to it in a little bit. Yeah, panic. Confidence will definitely be hit. But these are the kinds of passages I want you to work on. Most students are going to do well on the easy ones. We're going to do well on all of them. And method really plays a role. Road mapping, critical thinking, question method, all necessary to do incredibly well. And you guys are rocking and rolling. And you finished now the second hardest class in all of Kaplan, so you should really celebrate the fact that you have been doing a fantastic job as we're going along. Congratulations, my friend. And more, yeah, thermochemistry is a high yield section. It's worth practicing and worth speeding up on. That's why there's so much high yield in it. So you're exactly right. Make sure to practice it. It's why we hit it now versus later. That way there's time to build on it, especially with the holiday coming up. So you know what? It may not seem good now, but if we know it's high yield, it's up to us then moving forward to say, this is something I want to work on, this is something I want to improve on, and by gum, this is something I'm going to improve on. And science, that can feel fair. Since physics was so long, Gen Chem 2 typically feels hard as well, just because of time, especially since we didn't have a lot of time to relax and refresh. But no, it's good that we hit them before the holiday. That way you have time.